I know the diagram that you're referring to, but I've never heard that referred to as a beach ball. I can see why. It's a US thing. It might be a recent thing, because bear in mind I haven't studied this for 25, 30 years. So it might be a recent thing. Because when I was studying, that wasn't a diagram. You would look at literal seismograph data. So it might be a recent term that I'm not familiar with. There's exactly, the size of the planet is 35. There was a recent one. I don't know whether it was real, but I saw a social media post that was like, it was it this year or last year? There was a large asteroid that transited between the moon and the Earth, and so the gravity of the Earth captured it for a few months, and so we had a second moon for a little while, effectively. And the size of this asteroid was quoted in the American press as being the size of half a giraffe. Like, of all of the animals that you could use to visualize a potato-shaped object, why would you choose a giraffe? It's so un-asteroid-like in its topology. Yeah, like, which way do you slice it? Are you slicing it like this? Are you slicing it like legs under, head over? Like, which way? Surely like a hippopotamus, or a horse, or a cow, something round. A hippo would be perfect. How many hippos is it? Because hippos are about the same shape as an asteroid. Apparently we're getting a total eclipse soon, some point this week. Well, eclipses aren't a surprise. So, we'll have known about that for quite a while. Next one is 7th to the 8th of September is a lunar eclipse. 21st of September is a partial solar eclipse, visible in Australia, Pacific, Atlantic, Antarctica, which covers almost none of the Earth's population. So ain't no one seeing that one. So yeah, it's not that one. There aren't any more this year. That's it. We had the partial back in March, and that's it. Yeah, if you ask a physicist, giraffes are spherical, absolutely. You've read that there is an eclipse that will happen in August 2027. Yes, one of the longest that we have ever seen recently. Right. Shall we sort of begin? So, I don't know where this is gonna go. I've got some topics, like I've prepared a little list of things that I could go through. But basically, we can go in whatever direction you like. Because we can end up going down a number of different paths. Now, depending on which way we go, I'm going to have more or less expertise, because this is not my area of expertise to start with. But if we start talking about like wave dynamics, that's really not my area of expertise, although I know the basics. So yeah, we can go in whichever direction you like, but my ability to talk about it is going to be limited depending on which way we go. Yeah, I do have some like topics that I can fall back on if we run out of things to talk about. I'm not sure where to start. So obviously this whole thing has been triggered by the Kamchatka. I don't know exactly where it is. So the let's actually have a look. Where was it? I actually don't know the origin point. I know it was up here somewhere. Not helpful. Origin. Nope, that's the Japanese origin of the word tsunami, which we were about to cover. Can I just have a map? Please. All I want. Why is this so hard to find? Alright, let's do it another way, shall we? July 2025 earthquakes. Let's try it that way. List of earthquakes in 2025. This should have been updated. Magnitude. Here we go. Russia can attack. It was there. It's off of Yelezovo. That's alright, Hangman. I have Google. So this is the event that spawned me doing this, because I was asked to do this. I don't actually know that much about this specific event because I haven't read about it. But that's not my plan. Isn't to talk about this event. My plan is to talk about tsunami in general. But I can hazard a very good guess as to what actually happened here, just because of where it is. So that's what spawned this. Obviously, a couple of weeks ago, there was an earthquake here. It was an 8.8. It was very deep. And that spawned a tsunami which traversed the entire Pacific. And so we're gonna talk about that. But yeah, because this is literally a seminar MIP, so yeah, absolutely. So let's talk about, first of all, let's talk about the origin. So before I went live on YouTube, Hangman asked me, what is the origin of the word tsunami? It's Japanese. And the word means thrusting wave. So tsuru is the verb to thrust or to push. And nami is wave. So tsunami means a thrusting wave or a pushing wave. But the visualization most people have in their minds, because of popular media, especially movies, about what a tsunami is and what it looks like is mostly wrong. Most people, I think, when they're like, oh, there's been an event and there's a tsunami, I think what most people are picturing is a giant, like, cresting wave traveling across the ocean, like this massive wall of water, like pushing across the ocean and then like reaching a coastline and crashing down. That's not what it looks like at all. The dynamics of a tsunami wave are very, very, very different to that. And so if that's the mental image that you currently have in your head of what a tsunami is, just take that, dump it, and we'll start again, because that's not what they look like. In fact, if you were, so this particular tsunami started here, and obviously would have spread out, you know, this way. If you were in a fishing boat and you were down here, in amongst the atolls, going down towards Hawaii, if you were in here somewhere, like especially above the deep water, like here, this is several kilometers deep, maybe like 5-6K deep. this tsunami, as it passes your boat, you're not even going to notice. Because while you'll notice the normal ocean waves, and we'll talk about ocean waves in a minute, while you'll notice your boat going up and down on the normal ocean waves, which have a period of 3-4 seconds maybe, a tsunami has a period and a wavelength which is so long that it's not perceptible. Because down in the deep ocean, a tsunami wave, the wavelength can be tens of meters up to hundreds of, not tens of meters, sorry, tens of kilometers up to hundreds of kilometers. You can have a trough to trough or peak to peak distance for the wavelength of 500 kilometers, which is like the length of England. And you're not going to notice that on a boat. You're not going to notice that peak and that trough and that peak passing you over the course of an hour. You just can't feel it. So unless you're in shallower water, we'll get into that later, you're just not going to notice. You literally won't see it. So this wave, which is going past you and your little fishing boat, which is going to devastate a coastline somewhere else, it's going to reach Japan, or it's going to reach Hawaii or South America or wherever, and it's going to cause like meters high waves and devastation and everything. As it goes under your little boat, you don't even register it. Not visible at all. So make sure in your head that you don't have this idea of this wall of water, because that's not what it is. Very, very spread out lump, essentially, of water. Very, very flat, very long lump of water moving across the ocean. Is that when you event tsunami ships go out to sea? Yeah, in a similar way. If you think about how, I mean, most people have been to the coast, right? Or at least you've seen footage of coastlines. If you've spent enough time at the coast, you would come to realize that waves are only crest when they get close to the coast. You're not going to see a cresting wave, not in the same way as on a beach, right? So you might see little like white tips on waves in the ocean, but as the waves, these rolling waves that you see out in the deeper water, as they approach the beach, that's when they crest, right? And so you don't get that kind of like typical like surfer wave out in the ocean. It just doesn't happen. It's only when the wave gets into shallower water and some really interesting dynamics happen that I'll probably get into later, that the wave crests. And so in the same way that with normal ocean waves, if you're a surfer, for example, you'll use some kind of topological feature on the seafloor that creates like a gap in the waves, usually like a sandbar or something. So surfers will paddle out down one of these sandbars where there's no waves or fewer waves, lower waves. They'll paddle out behind the breakers, and then they'll kind of come back in towards where the waves just start to crest over, and that's where they start their surfing. To avoid your boat being caught in a breaking wave tsunami, but that's not always what happens. Or just generally just avoid being pushed around. Yes, if you take your boat and you take it out past that zone of the waves start to build up and gain effective power, it's exactly the same as a surfer paddling out into deeper water so they get past the breakers. It's a very, very similar situation. It's just that the scale of the wave is much bigger. And so the distance that you have to go out is much bigger. It only becomes a real wave. That is not true. What do you mean by real wave? I think I know what you mean. I think you mean a breaking wave. That's not necessarily the case. So again, this Hollywood picture that you have of this giant wall of breaking water. Like this big wall of water with like water like pouring off the top of it. That's just not what it looks like. So there are, I'll get into this in a second. It's very difficult to know where to start, but tsunami can arrive in two different ways, depending on what started the tsunami. Either the peak hits first, or the trough hits first. So, depending on whether the water was pushed up, or whether the water was pulled down to start the wave, because both of those situations are possible, will determine what arrives first. Does the lump of water arrive first, or does the trough preceding the lump of water arrive first? If you have the lump arriving first, which would have been the case for this tsunami, then basically what you see at the coast is just it's like the tide comes in really, really fast. So it's like normal, 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 normal water. And so the water, it doesn't like, it might sort of trip over itself a little bit at the leading edge, but it's more like it just, and this is why it's called a tsunami, a thrusting wave, because it does that. It doesn't do like, it's not like that. It pushes. It's like if you were to take a bucket of water and pour the bucket of water suddenly onto the floor, and you watch what happens to the water, it kind of just goes sploosh, right? It just kind of pushes out in every direction. What happens to the water at the coastline is a bit like that. So it just rushes inland. Because the energy that's in the wave in deep water, which is circular, becomes lateral for some reasons which I'll draw on a diagram in a minute. So that's what happens if the lump arrives first. There's no warning really if you don't have a warning system. And the water just pushes up the beach onto the land, over the trees, into the town or whatever. And then pulls the way back out again, obviously later. And that might happen a few times. If it's the kind of tsunami where the water has been pulled down first, I'll get into how they actually form. But there are two situations, push or pull. The water has been pulled down, like you take your hand in the bath or in a swimming pool and you put your hand underneath the surface of the water and you pull down suddenly, the surface of the water is going to dip down, right? If that happens, then the wave propagates outwards with the trough at the leading edge, not the lump at the leading edge. When that happens, first thing to arrive at the coastline is not the lump of water, it's the trough. And so what happens in those situations is the water pulls back first. So you might have heard these stories of, oh, we were on the beach and suddenly all the water disappeared. And my son, this was actually a real story from the New Year. Was it 2011? The New Year tsunami? Where a kid had recently had a geography lesson in school, British kid, I think. And they were learning about how before a tsunami, this particular kind of tsunami, the water pulls back first and then it surges. And that's exactly what happened. Was it 2004? Was it 2004? Holy crap. That was 21 years ago? Okay. So, am I thinking of Fukushima? Maybe. Anyway, that tsunami and many others, there are lots of stories about this. People who've been educated notice the water drawing out from the beach. So suddenly it looks like the tide goes out really, really quickly. And like much, much lower than normal. The reason for that is because the beginning of this wave, the trough, has reached the coastline. So you're seeing this part. And so the water pulls back. But of course, the lump is coming, right? And so because the wavelength is so long and the period is so long, because the period can be an hour, you actually have time, if you see that, if you see the water rushing out away from the beach, and this can happen all around the world, it's not just the Pacific, then you have time. Especially if you have access to a car, you have time to get in your car, shut the door, like grab the dog, and head to high ground. Or at the very least, just get as far away from the coast as you can. Preferably both. Preferably go up and away. And, you know, you have a bit of time to do that. And so there have been quite a few stories where someone has spotted this happening and has warned people. But it depends which bit of the wave is the propagating part, like the leading edge of the wave. If it's the lumpy part that comes first, not so much. The 2004 quake was so powerful it altered the Earth's tilt. Yeah, so that can happen. So we'll get into some of the earthquake stuff later. But basically, so it's like the analogy that often gets used of the spinning ballerina. So, or if you take an office chair and you start it spinning with you sitting on it, and then you have your arms out, and then you pull your arms in and you spin faster. When big tectonic events happen, what can happen is the rocks move around, and so they can push up or they can pull down, and that can actually change where the center of the gravity of the Earth is. Because you're moving such large pieces of rock around that it changes the shape of the Earth, it changes where the gravity is. And yeah, that can, if the average altitude away from the center of the Earth of the mass changes, yeah, if the average as it goes downwards, then the Earth will spin faster. The average as it goes upwards, then it would spin slower. And so yeah, absolutely. Big tectonic plate movements and the earthquakes associated with them over either very long periods of time or very short periods of time can alter the way the Earth spins, the speed of the spin, the axis of the spin, the amount of wobble. Just like if you take a spinning top and you prod the spinning top, you'll change the way that it wobbles. The Earth does that to itself. But it's important that you understand that the change that we're talking about is minuscule. It's not like you're going to suddenly wake up one day and go, oh, that's weird. That yesterday was only 23 hours. It's not that kind of scale of change. Like the scale of change you're talking about is tiny. Like it takes our most accurate clocks to measure these changes. If it pulls out so much you see the map the way it looks on the screen, how concerned should you be? Yeah, fairly. Is there a third option? What? So when you say a third option, so I would fit what you're saying into one of those two options. So basically, there's just two ways that a wave can be formed in that sense. So you've got the water gets pushed up or the water gets pulled down. If you drop something like this way into the water, so your example is ice, could also be potentially pyroclastic flow, something like that, or a big landslip that goes out and into the water. The force is being applied this way, but it's displacing the water. And so what that's doing is it's increasing the depth of the water immediately in front of the thing that's pushing. And so that has the same effect of lift the water up. So in terms of the wave that gets produced, the dynamic is the same as push the water up, even though the initial force is sideways. So I didn't cover, what I didn't mean to say, if I gave you that impression, was that there are only two ways that the wave can form. Like geologically, geomorphologically, there are many ways that a wave can be formed of many different sizes. But the effect is either essentially push the water up, pull the water down. So Seabank, it's really important that you understand that every change that happens on the Earth changes the Earth's rotation speed. When I stand up from my chair, I slow the Earth down. When I sit down on my chair from a standing position, I speed the Earth up. If I go outside into my garden and I pick up a big rock and I hold it above my head, I slow the Earth down. If I put it back down on the ground again, I speed the Earth up. This kind of thing is happening all the time. It's just that when really big events happen, then they are noticeable, right? These kind of things happen all the time. Like literally, if you do push-ups, when you push yourself up, you push the Earth away from you. The center of gravity, like the average center of gravity between the two of you moves. It's just that it's imperceptible on that scale. And so it's not that, oh, this big earthquake changed the rotation of the Earth. Everything changes the rotation of the Earth when it moves, if it moves vertically. Because all mass movement causes changes around it, right? It's just that it's measurable. When I drop a rock off a cliff, that's not measurable. But when a continent like springs upwards, that's measurable. And also obviously the time over which it happens. Your mama's so fat the Earth slows down when she stands up is literally a thing. It's just that it's not possible to measure it. Oh, it can be yeah, you could calculate it. You could absolutely calculate it. It'd be interesting to know what the difference is and whether it's like, is it I don't know, it might be on a scale that is down into like Planck lengths. It would be a tiny change. How do I think the Earth reacted? As you talking about Chicxulub? So, I don't know why I went that way. Chicxulub, which is here. So, there is a buried crater, which is here. It's about that big. And that is the hole that was made by the Chicxulub impactor, which led to the extinction of most of the dinosaurs. Not all the dinosaurs, most of the dinosaurs. There's some really cool documentaries on this because it's a very high profile event. And there are lots and lots of documentaries about how it was discovered and the geophysics of it, and so much study has been done of this now. How did the Earth react? So this impactor, we think, arrived at an angle. Most impactors will arrive at some kind of angle. And there have been experiments on the shape of the crater to determine, like, using ballistic models. So what they do is they take like a plate of usually synthetic material, so they can control the density and stuff. And they shoot ball bearings at it, and they try and replicate the shape of the crater that they're seeing in the real world to try and work out the shape and the speed and the angle and all those kind of things. And I forget the exact details for Chicxulub, but they, you know, the angle has been estimated. And so when this impactor hit the surface, which at the time would have been land, well, actually, it would look similar to this, actually. So the impactor was so big and moving so fast that it actually reached the mantle in part, or the effect of it reached the mantle. And so it went very, very deep. The energy involved is insane. And so a lot of rock would have just simply vaporized. And under those kind of conditions, solid rock can behave like a liquid. And so if you go and look at some simulations, I don't know if this is on, I never spelled Chicxulub. Chicxulub. That's a nice little Easter egg, Google. That's pretty cool. Can I do that again? I like doing the way it shakes. I like those Google things. If you Google dog or cat, you get a little button that you can press that makes it go meow or woof. Yeah. So we're here, right? So this is the current crater. It's partially underneath the Yucatan, and partially in the ocean. And we've gone in and we've taken cores and done all sorts of science on this thing. I don't think on here there's an animation somewhere of this. Yeah. So this is the impactor. A very basic animation of what's going on. You can see here, this is, I think this dark layer is representing the Mohovicic discontinuity, or the boundary between the crust and the mantle. And you can see it behaves like dropping water into a glass of water, right? So if you take a drip of water and you drop it, there's no ads on YouTube. If only I was streaming on another platform right now which didn't have any ads at all. Did you know I have a YouTube? Completely unrelated. I did not do that. Nope. I merely said, wouldn't it be cool if I was streaming on another platform that didn't have any ad breaks? And then I just also coincidentally happened to mention the fact that I have a YouTube. Because if I did do what Sam just said, then I'd be breaking the rules. My YouTube has no ads because it is not monetized. I make nothing from my YouTube. Or you can sub. Yeah, so these kind of energies looks a bit like when you take, if you imagine taking like a pipette of water and a vessel of water and dropping a drop of water in like slow motion into that container. It's going to look a bit like this. So it's going to form a dip. That's going to spread out, and then the middle's going to come back up again. Look, the middle comes back up. You get the splaying edge, the middle comes up. Sometimes you get that drop that comes off the top. All those things can happen with an impactor, with a rock. How would the Earth have reacted? Kind of depends on what hit, how big it was, what angle, how much of the ejector came back down to Earth, how much went up into space, because for the same reasons that we were talking about just now. If it's a very large impactor, that's got a lot of mass, which is obviously the important part, then, well, it's the important part in terms of what happens to the Earth afterwards. So if it's a huge impactor that has a lot of mass, just imagine a situation, this is not going to happen, but imagine a situation where that impactor is moving really, really slowly, and it impacts the Earth and basically just goes like crunch and just stays there, kind of sitting on the surface like a big boulder. Obviously that's going to have an impact on the Earth, because it's going to shift the center of gravity from our more or less spherical planet towards that impactor, and it's going to start making it wobble around a little bit. And also it's adding mass, and so that's going to do things to the orbit of the planet and so on. But collisions like that are very messy, and as you can see in this animation, when the impactor, this doesn't actually show doesn't show the impactor, but when the impactor hits, that material obviously kind of mixes in with Earth's own material. Some of it splashes upward, just like a splash of water. Some of it splashes upwards. A lot of that will fall back down underneath the planet's own gravity, or moon, or whatever it is. But some of that will actually end up in space. And obviously, any material that goes into space is lost by the energy system of the planet. And so it depends on the situation as to what hit, where it hit, what position on the Earth it hit. Because something hitting at the equator is going to have a different effect to something hitting higher up. And how much of that material stayed there. And how much escaped, how much got spread around the planet. Obviously, if it's a big impact and material gets sprayed up at escape velocity, some of that's just underneath escape velocity will spray up and actually end up in orbit. And then some of that will be just underneath escape velocity, and it will actually maybe go around the planet a couple of times and then land. Because it's just ballistics. So yeah, how the Earth would react depends. Another thing that can happen with a Chicxulub scale impactor is that the shock wave, because it's a huge amount of energy, can trigger all sorts of other things, because you're hitting a layer of rock which is butting up against other layers of rock that have all sorts of different dynamics and tensions set up. And so that impact and that shock wave can actually trigger movements. And so you can have, if you have an impactor which hits a plate which is subducting underneath another plate, and there's tension build up in this this boundary, the impact over here, which sends a shock wave towards that boundary, can trigger that boundary to slip. So not only do you have the shock wave from the impact, but then you also have events that chain off of that. So you have earthquakes happening where plates are suddenly moving because they've been jogged. Volcanoes going off because the magma suddenly gets jiggled, basically, and it breaks the seal. And this happened with the earthquake that spawned the tsunami a couple of weeks ago, where the shockwave from the earthquake triggered a volcano. And so you know, everything is interconnected, and if the shockwave is big enough, that shockwave is going to reach out and touch everything, and can set off some interesting chain reactions. And so things like volcanic events and big earthquakes, flood basalts, can happen as a result of impactors. And there's I think there's a theory linked to a few different massive volcanic flood events where you get lots and lots of lava pouring out onto the surface over potentially centuries or millennia that were, in theory, triggered by some impactor, which is really interesting. Yeah, and that had nothing to do with Tsunami really, but yeah. I forgot where we were now.
Merchandising!
I can't hear that because I got my headphones on.
Purchased, but
there is a giveaway in the Twitch chat.
Since it is a science
those of you who went over to those of you who went over to YouTube to avoid the ads, you're gonna have to come back. It is a mug. It is a Buttonassa mug. You would like to win a Buttonassa mug? JOIN. Thank you very much. A big bang for the mug. Joink. You already have one, but you highly recommend it. I don't have one of those. I need to get myself one. It's currently half full of coffee. Nice. Is it cold coffee? I have a pint of tea. Maybe I should enter. Maybe I should. It's warmish. Yeah, sounds like my tea. I also have I have what I thought was a flask full of tea. I don't think this is a flask. I think this is a single-walled water bottle. It's from Twitch. It doesn't keep things hot, and so I suspect it's actually, it looks like it's a double-walled flask, but I don't think it is. However, it is slightly warmer than this. So. It looks transparent because it's partially green. It's got kind of like, it's iridescent. It's got kind of like a blue side and then a green side. The bit you're seeing as see-through is green. Clarion. Congratulations, Clarion. You have won the mug. If you follow the link and you log in with your Twitch account so that it knows that it is you, and you go through and do a normal checkout, you will eventually, typically within a week, receive a mug from Seabang. Thank you so much, Seabang. That's very kind. On my to-do list for the next week, probably, is to get a whole bunch more merch done, and also to convert the mug designs for the new double size, so that you can choose between a normal size mug and a tall mug. That's going to be done in the next few days. See, I can see my house from here. In the brown bit. It's very brown. A bit orange up here. Right, we got sidetracked talking about Chicxulub. Right. What shall we cover off first? Might be useful to talk about a little bit of wave dynamics. We need to talk about subduction zones with respect to tsunami in the Pacific. I could go through briefly some of the different causes for tsunami. Yeah. The orange bit is on the other coast. I think he moves around a lot, doesn't he? Found in close proximity to golf courses quite a lot of the time. The Cheeto in Chief. I haven't heard that one before. That's good. I like that. Oh. I've heard Tangerine Toddler before. Okay. Let's talk a little bit about because we talked a little bit before about most people's mental image of what a tsunami is. And let me plug in my tablet of dreams. Bleh. This is a really old Wacom tablet. Mr. G uses Paint. If only I already had Paint open. Okay,
merchandising. Clarion Wolf purchased Badnassa mug.
Clarion, there's not as many color choices on that. You went for blue, sensible choice. I think your choices are like blue, other blue, or black. I think that's pretty much. I didn't want it to clash. Because I'm protecting you from yourself. Paint 3D sounds like a terrible plan. I can't say I've ever used Paint 3D. Like, I could use the drawing screen. Honestly, I was thinking about that earlier. Wouldn't it be cool? Because I kind of went to do it sort of instinctively. I was going to draw on here. And I suddenly realized, oh no, I can't draw on here. Maybe you can actually somehow. Oh, maybe you can. Kind of. Yeah, you can sort of draw things like that. Okay, so I'm not a fluid dynamics kind of person, but I know some basics. So most people's idea of a tsunami, like we were saying earlier, is that you've got your big ocean, and people are imagining. I'm not exactly sure what most people would be probably something like you got the ocean, and then it's like wave, like peak, down, jump, and they're imagining this thing going like that across the ocean, and this thing's like enormous, like a mile high, and like George Clooney's down here going like, oh my god, what are we gonna do? And that's what most people think a tsunami looks like, but it doesn't. Might be better off doing this in Photoshop. The massive wave miles from shore. Yeah, that's not how it works. So, on the scale of, let me just show you on the map. So on the scale of the planet, I go to a location that I'm familiar with. So, the UK, I mean, you can see the scale down there. The UK is a few hundred kilometers from north to south. So, like, you can see there the scale. So, the measurement thing. So, if I start at the south coast, the tsunami can have a wavelength of that. There's a bloke in the way? No, there's not. Oh, you can't see the scale. Oh, no, it doesn't matter. You can see this, right? So that's 400 meters. How do I get rid of that? No. How do I? Select a starting point. Select an end point with 400 kilometers ish. Can I not get rid of this? If I say done, it's going to oh, anyway. So, can you link draw tools to, I have no idea. If you can, let me know. So, yeah, so this, so if you start at the south coast-ish, And we're going up to, where are we here? Like North Yorkshire. Where are you? Can I have some labels, please? Is that Peterborough? Where's that? Darlington. Okay. So going up to the Yorkshire Dales. That is potentially the kind of scale of the wavelength of a tsunami. To put that on the context of the US, if you started in, let's say, the tip of Florida, down by the Keys, you would get to Orlando, roughly. So this is really hard to use. Not every wave, obviously, but this is the kind of order of magnitude of the scale of a tsunami in terms of its wavelength. So this is the distance from one peak to the next peak, or one trough to the next trough. So you have the wave will be like, and I don't mean water wave, like any wave. The wave will look like this. And the wavelength is from here to here, or from, you know, trough to trough, or any two similar points on the thing. You could also do from there to there, because it's the same. That is the wavelength. The time it takes to go from one peak to the next peak, or one trough to the next trough, in terms of if you're standing in a boat on the ocean, the time it takes for one peak to go past you and then the next peak to go past you, that's called the period. And if you go to one of my favorite websites, I love this, it's so good. Put the be careful if you share this, by the way, because if you share this from a machine that knows your location, by default it appears directly above your location and it puts the location in the URL. So just, if you share the link to this, just make sure you only take the beginning if you don't want people to know exactly where you are. So this is null school and it lets you interrogate all sorts of data. If I go to ocean and I go to waves, I think this overlay will tell me. So if I go to, you know, North Atlantic somewhere, it will tell me that the direction of the wave is 270 degrees, so it's going directly east. But the period of the wave is 7.5 seconds. So what that means is that the waves, if I'm a marker buoy or a boat, or I'm just floating in the water, it's going to take 7.5 seconds to go from one peak down the trough and up to the next peak. That takes 7.5 seconds. That's a fairly long period. If I come into the North Sea, 5 degrees and 8 seconds. That's very long. So 180 degrees and 15.4. Down here, like, there's some huge swell in the Southern Ocean. 240 degrees, 14.8 seconds, 9.17 meter high waves. And that's from trough to peak. In the Irish Sea right now, half meter waves, so not very big. And a 3.1 second period. That's quite much quicker, right? So for every one of these waves, sorry, for every one of the Southern Ocean waves, 15-ish seconds, then you would be getting 5 of these smaller waves. That's the period. The period of this can be an hour, right? So when you are on the ocean and a tsunami goes past you, like I was saying earlier, I need might do this in Photoshop so that I can have layers and I can just delete the layers, because otherwise I have to go like undo. So you're on the ocean and got the your normal sea waves. These are your sort of 5-second period sea waves on a human scale, where you can see them coming, and it goes up, and you go up and down in your little boat. On this scale, where you've got a boat that's probably going to be, like a fishing boat's going to be like that big. I can't even draw a tsunami on this scale. It's going to appear flat because it's such a gradual curve, because the curve is 200 kilometers. So from on a much bigger scale. So you've got the tsunami wave like this. That's pretty good, considering I'm drawing that with a mouse. So the lump, if you like, from there to there is 200 kilometers. The whole thing is 400 kilometers. This is 400. This is 200. It takes an hour to go from here to here, 30 minutes to go from here to here. So in your boat, to go up the wave, get to the top of the wave, and go down the wave, could take 30 minutes. And so you're just not going to see that. You're not going to feel it. You're not going to see it. All you're going to see is the normal ocean waves. And don't forget that, or make sure you realize, that waves interfere with each other, but they don't stop each other. So if you have, it's very difficult to draw this, but if you have, let's say I have a wave that looks like this, and I have a wave that looks like this, they're supposed to be exact mirror images. You get the idea. If you put those two things together, what you end up with is that. You end up with a flat line, because they cancel each other out. And this goes for water waves, sound waves, all sorts of waves, electromagnetic waves. They cancel each other out. Or, if it's not a mirror image, if I put two waves that look like this together, I would get a wave that looks like this. Because they add together, right? This plus this equals this. So, different types of waves on the ocean can exist together. So you can have a wave that is produced by a boat, like a wake. That wake can go through like normal wind-borne ocean waves, same time, like just crossing over each other. And then a tsunami can go through the area at the same time, and they all interfere with each other, but they don't stop each other. They'll add together, they'll cancel out, but the wave still goes through unaffected. And so when you have waves, and this can apply to tsunamis, later on I'll get to this, you have some waves, so if you imagine some ocean waves that are like doing this and they're proceeding, it's called a wave train. And then for some reason you have some other waves coming another way. You might get this on like a small pond where you have different things causing waves. Ducks. You watch two ducks, in the wake. When these two waves interfere, I'm drawing the peaks of the waves. It's going to look like this, right? So these waves are going this way, these waves are going this way. And so where you have, so this is a top-down view now. Where you have a peak and a peak, it's going to cause like an island. It's going to cause like a lump. And where you have a trough and a trough, it's going to cause like a crater. And so if you send waves across each other, they're going to amplify in some places and cancel out in others. Because when you have, like here, for example, you've got these waves are going this way. So this is the peak. It represents the peak of this wave, but it represents the trough of this wave. The trough goes this way. The peak's going this way, and so here, water's going to be like in a neutral position at this moment, because one wave is tall, the other wave is deep, and so they cancel out. And if the frequency of the waves matches, that point in the water will stay flat, because the two waves are exactly in opposition. And so the surface of the water at that position won't change. It's just going to stay there. And if you go and look at footage of wave tanks, there are some big wave tanks in the world, and they can set up these very specific frequency waves that interfere with each other. And they can generate these like grid patterns that look really weird because they just don't really occur in nature in that static of a way where you can just stand and look at it. And so you'll have these sort of like these peaks and the troughs, and it's kind of like oscillating around these areas of flat water, and the flat water is where the peaks and the troughs are cancelling out. So my point here is waves can go through each other and they will interfere. The amplitudes will add up and subtract, cancel each other out, amplify each other. The waves themselves don't get cancelled out by that. So if you have this situation here where this wave goes through and this wave goes through, the peak and the trough cancel each other out, that doesn't mean the wave stops. The wave carries on going through. It's just that at that point, peak minus trough equals 0. But then the peak carries on going, the trough carries on going, and everything goes through. So they're not interfering with each other. Beyond that one point. So, you apologize for being late to class. Can I please start over from the beginning so you can write it in your notes? No. Yeah, defenestrator, absolutely. So, I wonder if I can get a picture. These are all dramatizations. Should be able to find. There's an image. An image of a tanker which had a hole punched in the side of it. Is it this one? Yeah. So, rogue waves. I'm using the wrong word. So what can happen? You have all these wave oscillations. The waves are... Okay, so pop quiz. What are normal ocean waves caused by? I must press my voice. Yeah, it's fish farts. It is indeed fish farts. No, it's not. It's wind. The Rouge waves. Yeah, it's wind. So the wind blows over the surface of the water and it causes ripples, just exactly the same way that you get ripples in sand underneath flowing water. You get ripples in the water surface underneath flowing air. And those ripples, if the wind continues to blow, get bigger and bigger and bigger and bigger. And so a distant storm that happened hundreds and hundreds of miles away can cause waves which then propagate out over the surface of the ocean into an area where there is no wind. And so you can get this really weird situation where you end up with really big waves potentially reaching a coastline when there's virtually no wind. I've actually seen this myself. It doesn't happen very often. But you can get, like if there's a big Atlantic storm, for example, Western Europe can receive quite big waves that are really good for surfing on a day where locally it's very calm. because those waves were generated by wind that went a different direction and didn't reach the land. Or the storm, which goes faster than the waves, has actually already gone through. So you end up with waves being generated by different storm fronts and pressure systems. And so those waves can actually end up interacting. And if you have somewhere like the Southern Ocean, which is just this big circle, you've got South America kind of sticking down a bit, but the rest of it is just one big continuous circle of water. And because of the Earth's rotation and the Coriolis effect and things like that, the wind goes around and around and around and around, along with the currents. You can see here, these are the Southern Ocean currents. They just go around. You can end up with some really humongous waves building up because they just keep getting blown and blown and blown and blown, and they build up and up and up and up and up. So these are the surface winds currently on the Southern Ocean. Of course, it's winter down there right now. So 55, it's not actually that fast today. 72 is getting a bit quick. That's not gusting. That's the average speed. And so you can see this vortex pattern is going to drive wave creation. But then you also have these storm cells that are going around in the south of the Pacific, south of the Atlantic and the Indian Ocean. And those are also generating their own waves. So you have these waves which are being generated like around Antarctica this way. But then this will also be generating waves coming out from that. And those can meet. And so you'll have waves coming so here, for example, the waves are going to be propagating in this direction. The waves generated here are going to be propagating in this direction, and they're going to meet each other. Yeah? At least we could get into that. I want to try and stay vaguely on topic. But we could get into that because it's one of my favorite things. Because I love, let me just very quickly show you the jet stream, because it's really freaking cool. Hope today it's, yeah, here we go. So this is the jet stream. Have you ever seen the jet stream? The Northern Hemisphere today is not particularly strong. But the Southern Hemisphere is kind of crazy right now. Yeah, so this is that's the jet stream. 250 hectopascals. I think this is about, what's like jetliner altitude. I'm not exactly sure. It's like 30,000 feet? 150 altitude. 34,000 feet. That was not bad. Are you impressed? Yeah, so this is 34,000 feet, so the kind of altitude that jetliners fly at. One of the reasons that jetliners fly at this altitude is so they can use these winds, because if you are going, for example, from North America over to Europe, you can hop up here into the jet stream and you get essentially free acceleration across the Atlantic. Doesn't work in the other direction. If you want to go from Australia over to South America, you can use this jet stream here. Yeah, wind turbines 30,000 feet tall. What could possibly go wrong? So, let me go back down to the surface, where things are a lot calmer. So the waves being generated by the circumpolar vortex and by the storm cells that sit above that, they interact. And this happens. Won't necessarily be 90 degrees, of course, but where the peaks interact, they add up. So going back to the wave heights, right? So if we go back down to ocean, That's the best one for wave height. So down in here, yeah. So these are like 8.5 meter waves, 9 meter waves. So say 10, let's say 10 meter waves, which are not uncommon in the Southern Ocean. So you have two sets of 10 meter waves meeting each other. So 10 meters is about 5 humans standing head to toe to head to toe. When two 10 meter wave peaks meet, what do you get? You get a 20 meter peak. So as those two, if it was 90 degrees, those two peaks cross each other, where the cross is, you get this, you get a 20 meter spike. And where two troughs meet, you get a 20 meter trough. And so 20 meters from the bottom of a trough to the top of one of those peaks, that is a big difference. And the bigger the waves get, the longer the wavelengths get. And you start to get into the territory where the waves, which normally don't bother ships this size because the ship is enormous compared to the waves, and you'll have several wavelengths along the length of the vessel. So it all just basically averages out, and the vessel is really strong. Suddenly, you're dealing with waves that are the same height as the ship, or more. They're very peaky, because it's not a wave like this. It's a pinnacle, right? Let's see if anyone complains about ads. So yeah, so you end up with this pinnacle. So this idea of like these walls of water, that's not what we're talking about. We're talking about when one of these ridges meets another ridge coming in another direction and they add together. Because when they add together, next to that is an area where the waves are subtracting from each other, or sorry, are adding together negatively. And so you get this massive difference between these peaks. It's like a patchwork quilt, right? Where the stitches are is low, in between the stitches is kind of puffy, a bit like that. And so those peaks and troughs, and again, we're not talking about ridge-shaped waves. We're talking about like peaks, like meringue, right? If you make a meringue like that, if one of those peaks up underneath the side of your ship, this happens. And since the massive ship kind of transport industry has blossomed in the last century or so, oceanographers are starting to realize that these events are way more common than we thought they were. Initial estimates thought these kind of events would happen, you know, like once every couple of centuries, something like that. Now we're starting to realize these things happen all the time. And we have now very good satellite coverage about, or focusing on bathymetry, wave bathymetry. The bathymetry is just how deep something is. And so we have satellites that can actually measure in real time the surface of the ocean, and we're doing some really cool science with this. But one of the things that scientists are doing with it is they are getting a live picture of what areas of the ocean are doing dynamically. And oceanographers that are studying this have realized that these rogue waves, which are really peaks, so these rogue peaks happen all the time. Because if you think about it, like, how often is it going to happen that you've got like a storm cell up here and the circumpolar vortex here, both creating waves going in different directions? How often are those two things going to meet? All the time. in the Southern Ocean, there's always big waves, and there's quite often big depressions just north of that, especially in the winter. And the same thing happens in the North Atlantic, where you've got the trade winds going this way, and then you get storm cells up here. Same thing happens. And so these peaks happen all over the place, all the time. And it's only the fact that the ocean isn't completely full of ships that we don't see ships sinking all the time. It's just that the incidence of ship plus peak doesn't happen very often. But the more ships we put in there, the more it happens. And so we're starting to realize, and now we actually have the data of where these peaks are actually happening and how often they're happening. And we're starting to realize, ooh, okay, maybe we should make the ships better. Or you know, don't go there. Because these things are very, very destructive. I don't know, SBR, because it could be the case. I'm not an expert on shipbuilding at all, but it could be the case that one of the weaknesses of ships like oil tankers and container ships is the fact that they're so big and that they're so rigid. Because a small wooden sailboat of the kind that were used to explore the planet, you know, centuries ago, are small enough that if one of these rogue peaks happens, the ship basically just bobs up on the top of it and gets thrown around a bit. It's not like it's... Because the problem with this is that the ship is so big. My thing. So you have... How many undos can I do in Paint? Can I do enough? Hey. So, if you have one of these peaks, obviously I can't draw this in 3D, but you have one of these interference peaks, and you have like, so just to remind you, the scale of this kind of thing is like from here to here. That's going to be on the order of about 10 meters. 5 humans. With the full wave height down to the trough, because of course next to this there will be a trough. It's ridiculously small. Can I have that bigger, please? That's still ridiculously small. I'll switch to Photoshop. I'll do it. Okay. So then next to that, you'll get an interference dip. Don't forget, this isn't a wave like we were talking about before. This is like peaks and troughs, like a quilted quilt. The distance between here and here is also 10 meters, which means the distance between here and here is 20. Okay. But then you consider, like, how long is an oil tanker? How long is an oil tanker? 200 meters. So an oil tanker is 10 times this distance. How long is a, like, ocean-going sailboat from the 1600s? Not that long. Probably, I'd imagine it's on the same sort of scale as the wave height. So you've got a sailboat, which probably looks something like that in terms of its whole size, right? So if one of these rogue peaks appears to a sailboat, it's pretty big. And so what that means is that the sailboat is going to get thrown up in the air, and yet probably all the sailors are going to, like, go up in the air, and all the barrels are going to go everywhere. But the ship itself is just being lifted. Just like a big hand has come out underneath the ship and it's just thrown it up in the air or pulled it downwards. But the whole ship is underneath the same sort of strain because like literally half the ship is being lifted up by this peak. Problem with the tanker is that the tanker is, if I draw that in black, is 10 times this distance. So you're talking about a hull which looks like, you know, this. That's like a third of the ship. And so the problem is, it's going to cause stresses within the actual hull itself. Rather than lifting the whole ship, it's just going to punch part of the hull, which is what you're seeing here. Like it's just been punched, basically. Especially if the ship was like kind of rolling as it happened. Bang! Straight through the nose. And so the ship can't like rise up to deal with this wave because the rest of the ship isn't being affected by it, and you end up with this like tension and like local stresses. And the fact that the ship is made of steel means it can't bend and flex as much as a wooden boat can. And it just gets a hole punched in it. 31 meters. There you go. I wasn't far off. Yeah. And that was a pretty big sailboat, I think. So, so 20 is probably not unreasonable for a little trading. Grumpy, I'm not going to draw it like super accurately. I'm doing it in paint with a mouse. Please give me some slack. So yeah, that's how do we get onto rogue waves? So yeah, so this is the damage that a rogue wave can do. And these things are really, really popular. The point of this was, the whole point of this was, Tsunami essentially completely ignore the ocean waves that they are crossing. Because the ocean waves are happening on a completely different scale, and even if they do interfere, which they do, they're going to add up and subtract and so on. But they're on such different scales that essentially they don't interact. So you sitting in your little fishing boat off Orlando, as a tsunami goes past, you're not even going to notice. You're going to see the normal ocean swell, maybe a rogue wave. All of that is happening completely independently to the fact that there's this very slow, hour-long rise and fall of the tsunami as it goes past. And you will not see that. And going back to the question, or the comment we had like an hour ago, yes, when like a fishing village, for example, if they know there's going to be a tsunami, they will jump in their boats and try and get out to sea. Because the further away from the coastline they go, the deeper the water, the less effect the wave will have. Because if you can get out far enough, you get into the water where you don't even notice that there's a wave. And you have an hour or so, potentially. And if you are covered by the like global warming warning system, you might have 8 hours or 12 hours. Because if there's, and there is a really good warning system in most parts of the world, where they obviously track the cause and then they track the waves using various techniques, marker buoys and radar bathymetry, and so they know where the waves are and where they're coming and how big they are, and so they can say, okay, if you want your boat not to be wrecked, you should probably get out to sea, where you're safe, ironically. So JP, just going back to what I was saying just now and earlier, yes, there is footage of a Japanese Coast Guard cruiser going through that tsunami, and it looks like a what most people would think of as a wave. That is not what tsunami look like, or any waves look like, out to sea. They don't break. So a tsunami out in the ocean is this very, very hundreds of kilometers long lump of water that is completely invisible to a boat. Because it's on a scale which you just can't see, like the curvature of the Earth. From the surface of the Earth, you can't see the curvature of the Earth because it's just so big. Same thing. The curvature of the surface of the wave is so large that you just can't see it. So I don't want to get people to get the wrong impression of like a boat punching through a tsunami. That's not typically how it looks out at sea, because that's not how the wave dynamics work. Have I heard of the 1958 Lituya Bay earthquake? No, I have not. So, where do we go from here? So, you can't see tsunami out in the ocean. Ah, that's where we go. Wave dynamics. So, what is a wave? Let's do that. Oh, maybe. Hey. Does the tsunami wave lose energy as it travels long distance? No, not really. So, I'll talk about that in a second. We'll get into that now. Evander, thank you very much for the 33 months. I may lose my voice because talking like this without my headphones on, I'm probably talking a lot louder than I do normally. And I'm going to lose my voice, but that's okay. Other than that, I'm fine. It's good to see you, Evander. Thank you very much. Okay. I probably should put my headphones on. So, what is a wave? Defense strategy, we actually touched on that earlier, although I didn't get into the tsunami part of it. We'll come back to that. I want to cover the basics first. Turn myself down a bit. Yeah, unfortunately, it doesn't quite work like that. What is a wave? A water wave, specifically. Let me ask you a better question. In a water wave, so think of just an ocean wave, whatever. When you see, if you're standing on a cliff looking out to sea and you can see the waves coming towards the coastline or going along the coastline, in those waves that you are looking at, what is moving? And how is it moving? Because I think this is another common misconception that people have, because they've just not really thought about it. Thanks very much, Gen Exa, but I want to stay focused on the theory right now. I do vaguely have a plan what I want to cover. Okay, so the answer is the water is moving, but it's maybe not moving how you think it's moving. So when you see a wave on the surface of the water, take the ocean, what you're seeing is something that very like this, of course. And you see, yes, exactly. So the waves are propagating in this direction. So what you see is it feels like Google Earth is reacting to what I'm doing with the thing on paint in the background. The wave is propagating from right to left, but the water isn't moving. Sorry, left to right. Water isn't moving left to right. So when you're looking, I quite often do this with Live from the North, right? I'm not sure if it's doing it right now. It's an interesting little thought experiment. Let me just see if I can. I don't know if it's going to work today. Let me just change the camera. He doesn't have it zoomed in enough, and the water's not obvious. Okay, so sometimes on Live from the North, Tiger's cam view thing, you can see the waves coming past the camera, usually from left to right, as they enter the fjord at one end and travel down. And it looks, because you're watching these waves go past the camera, it looks like, and your brain will tell you, the water is moving from left to right. It's not. Or it might be. Probably it's not. The water could actually be going from right to left. What's moving is the wave propagation. So a wave is a movement of a medium, in this case water, but it's not movement of the medium in that direction. The wave propagates through, but you're not moving the actual material. If I bump a table, if I bump into a table with my hip, a wave essentially goes through the table and reaches the other end. It's just because the table is solid, the whole thing moves at once. But at a subatomic level, everything kind of squashes up and then releases, right? But I haven't moved, so if I bump the table and I move it 1 inch at my end, and it moves 1 inch at the other end, it doesn't mean that I've moved the inch of table from my end down to the other end. The wave propagates through the table doesn't move that much. So in water, so the wave is propagating in this direction, which means the wind originally was going in this direction to make that happen. What you see is a series of circles. If you put a neutrally buoyant marker of some kind in the water, so that it's floating in the water column. So you can put one on the surface, you can put one here, you can put one here, you can put one here. What you'll see is that the one at the surface is making a circle which looks the same as the wave. So it will circle, I can't draw circles, but it will do that. Okay? So the marker will kind of move forwards, it will fall down, it will go back, and it will go up. As you go down through the water column, those circles get smaller. And so the circle around this one is going to be a little bit smaller. Terrible circle. The circle around this one is going to be a little bit smaller again. The circle around this one is going to be even smaller. And the circle around this one is going to be tiny. And so as you go down through the water column, you feel that wave at the surface less and less and less and less and less. Until there comes a point where basically the water molecules are moving within their own kind of scale. And at that point, you could say effectively the wave is not doing anything. Essentially, it's infinite, but there comes a point where practically it's zero. So, in the Southern Ocean, where you get these 10-meter high waves, 15-meter high waves, but the ocean itself is very deep. The ocean might be several kilometers deep. Does the seafloor, if you're a clam, you're a little bivalve living down at 4 kilometers depth at the bottom of the Southern Ocean, are you even aware that there is a 15-meter swell 4 kilometers above you? No, of course not. Because these decreasing circles stop at a certain, effectively stop at a certain depth. And that's not going to be 4,000 meters. Any Southern Ocean 4-kilometer deep clams? Have you felt any waves recently? So what's happening as this wave is propagating is the water molecules are basically going in a circle. So if you, as I said, if you put the marker, this neutrally buoyant marker in the water and you just let go of it, and there are waves over your head for a diver, what you should see is, obviously you will go with it as the diver, but what you should see is that the marker goes in a circle. The waves go over the top. And if you move that marker down, you'll see a smaller circle. If you move it up to the surface, you'll see a bigger circle. So the water column is doing this. that is in deep water, essentially infinitely deep water, because once the circling stops, so you reach a point where it's completely stationary, it doesn't matter at that point. If the wave stops moving the water below a certain point, why we call it a wave, in a sense, yeah. It doesn't matter below that depth how deep the actual ocean bottom is, because this water here is not being affected by that surface wave. And this wave will propagate without being interfered by the surface of the Earth, purely the water moving. And so a question we had a little while ago was, does the wave, I can't remember who asked it now, sorry, but does the wave lose energy as it moves? The answer is yes, but not much. So when a wave is doing this, and it's just a gentle swell, and there's no like breaking at the surface because wind's getting underneath it or anything, it's just a nice gentle up and down swell, no whitecaps, that loses almost no energy. It's going to be maybe moving some stuff around, like fish, whales, boats, some waterborne sediments, things like that. Potentially that can cause some like friction. So if the water is, take the whale example, it's a kind of stupid example, but it's true. If the water is rubbing up against a whale, the whale has like inertia in the water because it's quite big, and the waves are kind of churning around different parts of the whale's body. That's going to be creating friction up against the body of the whale. That's going to heat up the whale. When two things rub past each other, they heat up very slightly, imperceptibly, but very slightly. And so these waves will be losing a little bit of energy here and there, but essentially none, for all practical intents and purposes. And the bigger the wave, the more efficiently they move up to a certain point. And that point being when they start interacting with the bottom. Whales, yeah, if we just had solid wall of whales, that is the solution. So we should start breeding really tesselatable. What is the most tesselatable whale? Do we have any whale species that fit together really well? So the whales have a thick layer of fat on their skin to protect them from heating through rubbing with waves. I'm going to regret saying that. They are, however, covered in barnacles. Sperm whale, very square heads, exactly. So we'll stack them head forwards like bricks. Yeah, cool. How did we get onto that? So yes, waves do lose energy, but when they're in very deep water and they're not interacting with the ocean bottom, they don't lose very much energy. And so these waves, so if you have a tsunami, just traveling across deep ocean, it can go a long way. So going back to the Yucatan event, so right here, caused a tsunami which spread out over the Pacific. That wave, that tsunami wave, can easily reach over here. If there wasn't any land in the way, if the entire planet was just deep ocean, that wave's going to go around and around and around and around. Obviously, there's no way for it to start, but thought experiment. If you have a tsunami level wave, it's just going to go around. It's going to go around and around and around until it loses enough energy to dissipate. But that's not the situation we have on Earth, because we do have land masses, and the ocean bottom is not infinitely deep, and a tsunami wave is quite big. I don't know, on Google Earth, can I get a seafloor map? That's something I can do. Add data layer? That's probably going to ask. Ooh. EV charging stations. Rooftop albedo. Oh my god, I love rooftop albedo. Some cool stuff in here. Terrain elevation. Was that a thing? Oops, no, wrong one. Add data layer. Did you see the terrain elevation? Elevation contours? Or maybe. Oh, upgrade. Is it a paid feature, Google? Is it on maps? I'm sure there's a way. I don't. If I knew how, I would. If anyone knows how to do it, please let me know. I'm just not seeing a checkbox for like remove the ocean. And all this is like paid stuff. Or you could do it on Google Earth. The satellite layer? Oh, yeah, yeah, thank you. Yeah, yeah. I knew I'd seen it somewhere. So. So Pacific. Pacific is really deep. So from the Kamchatka Peninsula here, where the earthquake happened, the wave would have propagated out from the south coast here in this direction. And potentially actually from the other side as well, this way. And it will have mostly been going over deep ocean, but the ocean is not uniformly deep, and a tsunami is really, 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 really big. Hi. What is hi? Oh, Hawaii. Hi. It's like, why does it say hi in the middle of the O? I didn't realize that the state abbreviation for Hawaii is hi. That's funny. So most of the time, the wave is going over very deep ocean, but tsunami are huge. So if you imagine the... we were talking earlier, you can do some maths. With a tsunami, this wavelength can be hundreds of kilometers. So a really, really big tsunami from here to here could be 400 kilometers. That's a really big tsunami, but let's go with like 200. So if this is 200, oh no, we're about to do maths. This is 200, so from trough to trough, let's say the wavelength is 200 kilometers. That means that the distance, so how do I work out? I guess that would be the diameter of the circle, right? Yeah. So you've got a circle underneath that, which is the surface oscillation of the wave, which reaches down hundreds of kilometers. And of course, the ocean is not that deep. It's only 4 kilometers, 8 kilometers. Yeah, sorry, everything's going to be metric. You're going to have to convert yourself. So while that rise and fall happens over a long period of time, it's quite a big rise and fall out in the deep ocean. And that circle goes down and down and down and gets smaller and smaller and smaller, absolutely touches the bottom. But the ocean is very deep, and so it's a minimal interaction. And so the wave is going to propagate out without losing much energy until it gets to shallower water. And so what happens with these circles as you get shallower, I wish there was a big eraser in Paint, because I don't want to use this little thing. So we have to. Actually, let's I should have just used Photoshop. Let's draw an ocean bottom here. Draw a big white square. Oh, I could do that. Yeah, that's true. It's alright. It's okay, Molly. I'm glad that you're excited about how to use MS Paint. I appreciate the enthusiasm. Yeah. So if you have an ocean bottom, which is underneath this interaction distance for a normal wave. So we're not talking about tsunami now. We're just talking about normal ocean waves. So you're like your 5-10 meter waves. And as that wave approaches the coastline, the ocean bottom comes up to the surface. Obviously, lots of different topologies are available for coastlines, but at a very basic level, it looks like that. And then you got your little beach in here with your people sunbathing and whatever. What's going to happen is as this wave and this circling approaches the coastline, and obviously the bigger the wave, the further out that is, but for your sort of like nice beach holiday kind of 1 meter waves, that's quite close to the shore. And so here we're talking on like human scales. We're talking, you know, this might be, it's not going to be like 2.5 waves to the coast, but like 100 meters, something like that. At some point during that 100-ish meters, the waves are going to start to feel the bottom. So this circling is going to start to impact the sand. What happens then is really interesting. So there's some very, very, very complicated fluid dynamics that goes on, which I am not capable of explaining the maths for. But what starts to happen is the wave essentially sort of, think of it as tripping up over itself. So if you are, if you're running and you catch your foot on like a root or something, you start to fall forwards and stumble, and like your feet are still going underneath you, but you're kind of falling forwards. It's a bit like that, because the top of the wave, these circles are not feeling any resistance. These ones are feeling resistance, and the whole wave, once you get to here, whole wave starts to sort of trip up over itself and do this. Okay. The feet of the wave are catching on the ocean floor or the coast. And the head of the wave is falling forwards, because it still has that momentum. The bottom of the wave is starting to drag the sand. If you've ever gone snorkeling or diving, you will have seen the wave action above your head pulling on the sand. You literally see the sand going backwards and forwards. That motion of pulling the sand back and forwards takes a lot of energy out of the wave, because you've got the sand grains are grinding up against each other and grinding each other down. That takes energy. And that friction takes energy out of the bottom of the wave. And then you get things like kelp, right? You get kelp growing, you get seaweed growing, you get coral reefs. Pushing water through moving kelp and through coral and things like that. It's all taking energy out, because the wave is moving that material around, whether it be organic material or inorganic material. And that's taking energy out of the wave. But that's not taking energy out of the top, because the top is still just in normal water. And so the top keeps going. And the wave starts to trip over itself. And that's when you start to see the breakers. Because this circle starts to elongate and elongate and elongate to a point where the top of the circle is going much, much faster than the bottom of the circle is retreating. And that's when you end up with the breaker. That's when the water starts to get that lip on it, and you get the white froth at the edge, and it crashes down because that circle breaks. There are ads coming up in 1 minute. Coincidentally, I have a YouTube completely unrelated to that comment. If you would like to go and check out my YouTube, you can. There's ads in about 39 seconds. Thought I'd mention that. So that's how waves, like your traditional beach holiday waves, like surfing waves, that's how they form at the coastline. By tripping up over themselves. And that circle basically breaks down. And this round and round motion, so don't think of a wave as going up and down, it goes around. This around and round motion gradually turns from this into sort of this. And eventually that circle breaks and it just becomes a pure in and out motion. So if you think about once the wave actually breaks, it pushes up onto the beach completely laterally, and then it pulls back completely laterally. Okay, so you go from circle, 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 wax on, wax off, to punch, essentially, to put it in Karate Kid terms. You go from wax on, wax off, to punch. And what that is, it's just a change of direction of the motion. So instead of seeing the whole circle, you're seeing the circle get squashed and squashed and squashed and squashed and squashed until you're only seeing the back and forth. Okay? That's how like a beach wave forms, a breaking beach wave. Okay? Exactly the same thing can happen with any sized wave. So if you have your little itty bitty, oh, there's just a bit of a breeze on a lake kind of waves, where there's been a bit of wind going over the surface of a big lake, and you get waves, but they're not like ocean waves, they're just tiny little waves. They have very short wavelength, they have a very fast frequency. And they're traveling along. They don't know they're small waves. They just, all they know is that they're waves. And so they might cause breakers as well. And if you go to a little pond, like a duck pond or a lake, if it's a windy day, you might see breakers on the beach, right? But they're not the same scale as a beach wave. They look the same. It's just that the scale, like from the breakers forming to the waves breaking on the beach might be like this far. Whereas on the scale of a big beach that faces the ocean, the scale is more on like hundreds of meters. And so this wave dynamics, wave physics, scales up to any size wave. There will be a point where you get down to tiny little movements which actually start to interfere with the physics of the water molecules themselves. At that point, it breaks down. But on all human scales, it works the same way. So, I'll just wait, just in case anyone isn't bright enough to go and find the other stream. I will wait until the ads are over. Have I already arrived at the point where lateral size translates? That is literally what I'm explaining right now. Yep, that is literally what I am explaining on the screen right now. So, on a duck pond, the waves as they approach the shoreline, you don't think of it as a shoreline, but as they approach the edge of the pond, if you've got a little muddy slope there that goes down into the water for the ducks to get in and out, there's going to be breaking waves, and if you zoom right in with a little macro lens, it's going to look the same if you slow it down as a beach wave. Small beach waves, if you zoom in enough, look like big beach waves. Big beach waves, if you zoom in enough, look like really big beach waves. They all look the same. It's just the scale is different. And so Dutch actually puts it a really good way, which is the bigger this circle is, the bigger this in and out movement is. So if you have, going back to the duck pond, if you have a circle which is literally this big, so however big that is on your screen, think of it as being literally that big. So the size of a coin. You can imagine the wave that produces, right? Produces a wave that is on the size of a coin going up and down. And so the lateral movement you get from that when it washes up on that little muddy bank is going to be on that kind of scale. It's like a squashed coin. And there's some very, very complicated maths to work out how much movement that is. But it's on that kind of scale. So, you know, a coin-sized wave is going to produce a rush up that muddy beach of maybe like that big. But as you scale up the size of this circle, you scale up the size of the in and out. So when you get up to a wave which has a trough to peak height of 1 meter, instead of talking about coins now, we're talking about like beach balls, big beach balls. And the in and out that's going to produce is more like you would typically see on a beach. You imagine meter-high waves. So what you think of as the wave height is probably actually half of the wave's height. So I'm talking about waves that look like they are 50 centimeters high. You imagine those kind of like gentle beach waves. Think in your mind now about how far up a beach. Beach has different gradients, but just imagine a beach. Fairly flat beach, preferably. Just imagine beaches that you've seen with those kind of height waves and how far up the beach they wash. Depending on the grade of the beach, a few meters, right? So like nice gentle like paddling waves that your kids are going to have fun playing in. Not surfing waves. They're going to wash in, I don't know, like 4 or 5 meters, something like that. And then pull out again. If you get up to like surfing size waves, so you're talking like 3, 4, 5 meter waves. How far did those wash in up the beach? Maybe like 20 meters, 30 meters. Because this circle gets translated, the energy in the circle is much bigger because it's a much bigger circle. And so that gets translated into a lot more lateral energy because there's just more energy there and it has to go somewhere. You can stop assuming that you're a clam. Yeah. You can imagine that you're some kind of beach worm now, like some kind of sandworm. Like you can imagine that you are what are they called? A gooey duck. Imagine now that you are a Northwest Pacific gooey duck. Resting in your little sand burrow. So, bigger wave, bigger circly wave out in the deep ocean translates to more in and out at the coast when that wave reaches the coastline. And I'm sure you can see where I'm going with this, because then when you get to the scale of a tsunami wave that has a wavelength of hundreds of kilometers potentially, the amount of energy in that wave. Imagine, all right, so take the amount of water. So if you stand at the beach, and you would go back down to like the paddling waves. So you've got like let's go down a bit. So like shin high waves, paddling waves, you know what I mean, right? Nice beach holiday waves. Imagine standing, looking at the waves. And you have your feet like shoulder width apart, and the waves are going through your legs. The water that's going through your leg, like the lump of water that's going through your legs, you're weighted out a couple of meters, is going to be about the same volume as a bucket of water. Okay? Can you imagine that? So if you managed to like catch the wave as it went through your legs, the volume of water you're talking about is about a bucket of water, approximately. And you can imagine if you're out in the swell part, so you're sort of paddling, maybe like chest deep, and you're in the swell, you can imagine how far up and down that bucket of water is going. So it's going, you know, like this far, foot or so. Imagine now standing with a full bucket of water, going up, down, technically in a circle. So going circle, circle, but essentially up, down, up, down, up. That's a good workout, right? Imagine how much energy it takes to lift that bucket of water, like 20 liters of water, up and then down every 3 or 4 seconds. Up, down, up, down. You're going to be really tired pretty quickly, because that's how much energy it takes to lift that wave up and down. That's how much energy is in the wave. You'll do the down part? Okay. What you'll also notice in that situation is that you can really feel that circling motion. You might have noticed this if you've done a bit of like paddling, snorkeling near the coast, you can, or just jumped off a boat, you can really feel that circle. You will have probably noticed pretty quickly that you're not just going straight up and down. You're doing a circle, and that there's not much that you can do to stop it. If you grab a boat that you're, you know, snorkeling off of, you can't stop yourself from moving in that water very easily, because the water has so much energy it can just throw you around. Imagine now, metaphorically speaking, if you were a giant standing in the Pacific Ocean as a tsunami goes across it, 200 kilometer wavelength. And you've got the biggest bucket you've ever seen. And you try and catch that wave, that one wave, as it goes through your legs. Your legs are maybe like half a wavelength apart, so your legs are like 100 kilometers apart. And you have a 100-kilometer diameter bucket. And you're trying to catch that wave. Imagine how much energy it would take for you to lift that wave up. That is how much energy is in that section of that wave. As an analogy. It's an insane amount of energy. Water is really, 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 really heavy compared to air. So you think about the damage that strong wind can do, the amount of energy that's in fast wind like hurricanes and tornadoes is nothing compared to water. Floodwater, fast-flowing water, you get into a river. You get into a river, not a particularly fast-flowing river. If the water is flowing at like a walking pace, and it comes up above your knees, you will not be able to stand up. It will just knock you flat. Flowing water is insanely strong, insanely dangerous, and insanely destructive. It will just go through a building like it's not there. Because while to you and the wind, a brick wall feels solid, to the water it's nothing. And but Sammy, did you not hear me say earlier that in the deep ocean, if there is a tsunami, you won't even know it's there? So one of the challenges for the Pacific bucket holding giant would be even seeing that the wave is there. Two feet even fast, yeah, exactly. And the amount of energy that contains is crazy. You know, you pick up one of the pebbles from the river and look at it, like look at how round it is. Think about how much energy would go into knocking a rock into a sphere. Crazy. Or picking it up. You take like a 1 kilo rock. How much energy would it take to pick up that rock and flow it downstream? A lot. So, just recapping quickly. Waves make circles in the water. If the ocean is deep, the waves don't feel the bottom. When they do start to feel the bottom, they start to sort of trip forwards, and that circular motion translates more into a lateral motion, and that's how you get the waves pushing up onto the beach. And that scales up, and tsunami feel the same thing, but they are obviously going to feel the ocean much, much shallower. So a tsunami that is traveling across a deep ocean is going to be traveling, so you've got a wavelength of hundreds of kilometers potentially. It can be shorter, but hundreds of kilometers. The period is going to be an hour, tens of minutes to an hour. So it's going to take the wave, going back to my UK scale, right? So we were saying like the wavelength of a tsunami could be as long as, on the top end, could be as long as like the south coast up to North Yorkshire. It's going to take about an hour to travel that far. What else travels that far in about that time? Passenger planes, right? So a passenger plane travels at hundreds of knots. Yeah, a passenger plane travels at hundreds of knots. A tsunami also travels at hundreds of knots. And that is much faster than a typical ocean wave. So a typical ocean wave is traveling like at the speed that someone runs. So a few miles an hour, a few knots. Tsunami is traveling much, 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 much faster. But again, don't have this picture in your head of this huge wall of water going at 500 miles an hour. That's not what's happening. It's a very, very slight lump of water that takes a very, very long time to rise. That very slight rise, the peak of that, or any point of it, is traveling forwards. That wave is propagating at hundreds of kilometers an hour. And so you can then calculate how much time is it going to take to go from the origin, which recently was here. How much time is it going to take to travel from there over the ocean surface to, for example, the coast of South America, South America, or Hawaii, or Guam, or wherever. And you can do that calculation. So you can take the, if I go back to Google Earth, take a ruler, you can just measure. You can just go, okay, from there, go to Australia, Brisbane. How far is it to Brisbane? It is about 9,000 kilometers to Brisbane. And so you can just do the maths, and that's going to take many hours to do that, that distance. And so the people in Brisbane, if they were to get a tsunami warning from an earthquake that happens around here somewhere, are going to have as long as it would take someone to fly from the origin down to Australia. Maybe 12 hours, maybe more. This is why tsunami warning systems are so incredibly important for saving lives. It's because there can be an earthquake up here, and okay, the people up here are kind of going to feel it immediately. The further away you go, the more time you have. So the reason this was so dangerous potentially for Japan was, of course, it's not very far away. And so down here, you're talking about a few hours, like 2 hours, 3 hours, 4 hours. So maybe like 2-3 hours to the top of Hokkaido. But people over on the other side of the Pacific, so the coast of the US, Canada, Alaska, further away you go, the more time you have. And so those tsunami warnings are really, really important because people who live far away have loads of time. You're living in Hawaii, so let's go back and do that again. Let's calculate. So from the origin roughly to Hawaii, 5,200. So you can do the maths. So 5,200, let's say the tsunami is traveling at 400 kilometers an hour. That's going to be, I did that wrong. 13 hours. On that kind of order of magnitude. So in Hawaii, when this went off, they had that kind of scale of time. And so you can pack a bag, get some water, take some food, you know, even like pop down the shop, buy some bottled water, buy some instant noodles, buy some camping equipment. Like you can literally do that. Obviously everyone's going to be trying to do that. But you have time to get in a car, you know, go and drive up a mountain, sit in traffic. But you know, at the very least, if you live somewhere like Hawaii, like you can walk quite a long way in 12 hours. So even if there is traffic, you know, the topography of Hawaii. Can I get rid of? Can I? Map. Can I do terrain? Can I do terrain for free, please? Is that a thing I can do? Nope. Screw you, Google Earth. Fine, we'll do it this way. If you're in Hawaii, let's say you're in, is it Hilo or Hilo? I never know. If you're in Hilo Bay, you have a beach apartment, you can just start walking. If you absolutely have to, if like the airport's closed because it's all busy and like you know, your car gets stuck in traffic, you can literally just get out of your car and start walking, and you can just walk up into the hills. Because the higher up you go and the further away from the coast you go, the safer you're likely to be. Hopefully you can get away in the car, and as long as you go interior a little bit, totally fine. Because the scale of the kind of tsunamis that we get from earthquakes, which are very common in the Pacific, are not going to reach that far inland because the sort of vertical height you're dealing with is not that big. So I think from this 8.8 magnitude earthquake over here, I think they measured, I think the highest wave, which would have been trough to peak, was 4 meters. And so, yeah, that translates to quite a long way inland. But it's not that far inland. And if there's like hills involved, obviously it's much, much less. You get a steep hill, go up that, you'll be fine. $250. Yes, so what can happen, and the reason that I picked Hilo Bay here is that what can happen is that if you have a wave, so you'll notice that this bay is sort of like a 90-degree angle. If you have a wave coming in from this direction, it starts to focus because the wave kind of piles up against the rising seafloor, and it kind of channels it inwards. So if you imagine having flowing water and you kind of take your hands at an angle and you do that, the water kind of like rises up in your hands as it tries to figure out where to go and get through the gap. Same thing happens. So the wave starts to pile up, and all the energy that used to be out here gets narrower and narrower and narrower. Some of it obviously interacts with the coastline here and gets dissipated. But some of it gets kind of channeled inwards, and you can actually end up with that energy being concentrated. And so if you have bays that are kind of this shape, or you have underwater canyons, for example, like the ones off Portugal, so this one here is very famous, for example. So I think someone mentioned it earlier. So this canyon here produces some of the best surfing in the world because it channels deep ocean waves and allows them to come all the way into the coast. So both it's enabling the energy of the wave to get closer to the coast without being dissipated by the shallow ocean floor, because it's deeper. But also the canyon itself acts as a focus of some of these waves, because the energy needs to go somewhere, and so it's sort of piling up on the shallow coastline. But it sort of falls off, if you like, into the canyon, and where it can move more freely. And so it pours, literally pours over the sides of the canyon and piles up in the canyon and moves towards the ocean, the coast. And so you get these amazing waves at the beach. I wonder if Google Earth captured any. Nope. Flat as a pancake. Hello, doggy. Oh, little white poo dog. Yeah, this beach is renowned for surfing, but not on this particular day, apparently. July 2021. Nothing. It's kind of crappy weather for July. So yes, the energy from waves, including tsunami, can get focused if you have some kind of estuary or inlet or bay, underwater canyons. Then yeah, that can focus the energy, and you can end up with pretty horrendously destructive energy reaching the coast. Was it 4.9 feet? Okay, yeah, so that's what, 1.4 meters, something like that. No, a bit bigger than that. 1/6. So surfing in a tsunami is not really possible, because tsunami don't really break like a beach wave does. In certain places it might do, but the coast, from the point of view of a beach wave, like a normal surfing wave, is quite a different shape to how it is on the scale of a tsunami. And so while a beach wave kind of rears up and breaks over itself and splashes down and then rushes up the beach, that's not really what a tsunami does. So a tsunami, if you're standing at the coastline, what you'll see, like I described hours ago, is either, depending on what arrives first, either the water will pull back and then push, or it'll just push if the peak arrives first, depending on how the propagation started. And so what you see is more like a very sudden tide. So, you know, I don't know if you've ever been at the coast when a sudden wave comes, like a wave that you weren't expecting, and every now and again you get a wave that's a bit bigger than the others. And yeah, it might break and stuff like that, but ignore that for a second. You're standing on the beach, and you're standing where you thought was just onto the dry part of the beach, right? You've been watching the waves for a few minutes, like coming up to your feet. And then suddenly, there's one of these waves that's just bigger than the others, and it goes woof, and it rushes right up the beach, goes over your feet, soaks your feet, and goes meters behind you. That's what a tsunami looks like. If you ignore what happens a bit further out, the rushing part, that's what a tsunami looks like, on a much bigger scale. And so what you will see, if you are standing like on a cliff or something, looking out at the sea, and a tsunami arrives, as I said, you'll either see just the water starts to come up, or it'll go down first and then come up, but you won't see a wave. You don't see like the movies. You just see the water just come up and come in. So suddenly, the water is like just pushing in at the coastline, and it will come up the beach at quite a pace, come up the beach, push into the buildings, the hotels, go down the roads, and of course, you know, it behaves like water, and so any low points, channels, you know, gaps between buildings, you know, culverts, rain ditches, that's where the water's going to flow. Yeah, I'm trying to avoid showing stuff that's other people's copyright, Yak. I could like go and show loads of videos, but I don't want to do that because it's not mine. But you can go and look up, easily find footage of tsunamis. There's loads and loads and loads and loads of footage of tsunami. Just make sure it's real. In the age of AI, just please make sure it's real before you go, oh look. So yeah, so what you see is this rushing inundation. That just keeps going. It's like the mega tide from hell. Because if you think about it, so the tide, where the moon's gravity is we're going to use shapes. Learn how this works. So the tide, very simply, is like on this kind of scale, right? So this is the Earth. Oops, that is way too big. But you get the idea. That's too big as well. But you get the idea. Let me make that slightly more sensible. So the tide is two bulges of water, very, very simply, two bulges of water opposite each other that go around the Earth. Or more accurately, the Earth turns underneath the two bulges of water. Better way to think of it. The scale of... You love my paint skills? I know, right? So good. The scale of a tide is not dissimilar to the scale of a tsunami. A tide is a lot bigger. Because if you think of this like a wave, it's not really, but if you think of this like a wave, this bulge, caused by mostly by the moon, of course. You got the moon over here. The moon plays with it a bit. The moon causes it. So this bulge that's being pulled towards the moon, the kind of scale of this is thousands of kilometers, like that kind of scale. Let's say like 2,000 kilometers. So it's on the same kind of almost order of magnitude as a tsunami. So tsunami is like 200 to 400. That's a significant percentage of this. And so a moving tide is going to behave at the scale of our topography very similarly to a tsunami. Tsunamis and tides are going to behave kind of the same. And so if you've ever been at the coast, been on a beach holiday, lived at the coast, stayed at the coast, and you've seen a tide come in and out, you'll be kind of familiar with how that looks, especially if it's an interesting coastline that has inlets and channels and things that fill up. And so if you're maybe at a harbor, maybe the harbor goes almost completely dry and muddy and all the boats, you know, sit on the bottom, and then when the tide comes in, the height of the water goes up by a couple of meters, and then all the boats are floating and you can't see any of the mud. And maybe you've seen tide coming in over a very flat area of mud, where it comes in very quickly. It comes in at a pace potentially faster than a human can run in some places. That's very, very similar to how a tsunami works. And so, and what I was talking about earlier with the focusing up channels and things like that, that's exactly the same as how a tidal bore works. You get a tidal bore because the tide goes into some kind of channel. So, for example, one that I know very well because it's very close to me, the Severn Estuary. So this is the river. This is the River Severn, and it empties into the Severn Estuary and becomes the Bristol Channel. So this is a very long, narrowing estuary, and the tides which come up the Bristol Channel get focused and focused and focused and focused, and what you end up with is the water tripping over itself in a very similar way to the way that a tsunami works. And it's just a lump of water which pushes up through the estuary all at once. That's pretty much exactly the same. So just scale that up a little bit, put a bit more energy in it. That's a tsunami. Don't think of it as a big wave in the sense of like beach wave. Don't think. What was that result for? No. What? Why am I getting hair? Hello? Okay. Never underestimate the power of the minus in Google search to remove things you don't want. Okay, apparently that's a hairstyle. Don't think of the tsunami coming to the shore like that. Think of it as a big lump of water which just goes woof. I don't think I've got any images of, well, I don't really want to show video. I'm kind of happy showing, yeah, there we go. So, so it looks more like a flood, right? This is a huge lump of water, hundreds of kilometers long, that all arrives all at the same time. So the front of the lump arrives and the lump just keeps coming and keeps coming and keeps coming. And so it looks like this. It doesn't look like that. Don't have that in your head. And it does things like that. Like I was saying earlier, Molly, it's like, imagine that you had a bucket of water and some kind of solid floor, and you just upend the bucket all at once. Like imagine like zooming in on what that water looks like as it hits the water and then go thump sideways. It's that sideways motion, or that just like lump of water. That's what a tsunami looks like. So breaking we've already covered. If you want to go back in the VOD later, I've erased it now. But so basically, breaking is caused very, very quickly. But I did cover it earlier. If you want to go and look at it, and don't forget, I do have this going. This is going to YouTube as well. So if you want to scrub through YouTube later, or now, then you can do that because it might be a bit easier than scrubbing through it on Twitch. Yeah. So basically, it's caused by the wave touching the bottom. So the wave at the top is making circles. Actually, that's works quite well. The wave at the top is making circles. Why didn't I do this earlier? Oh, because it's actually really hard to use, that's why. is impossible. So the wave is making ever decreasing circles. I can do this. Oh god, that's terrible. Okay, this is supposed to be a straight line. Imagine that vertically. The wave is making circles, circle motions. Then when that intersects with the seafloor, as the wave travels inland, it starts to trip up, basically. And that circular motion gets squashed and becomes a more lateral motion. And it's the wave tripping up over itself that causes it to become a pushy wave rather than a circly wave. Right. We haven't touched on the geology at all. We've been talking almost purely about wave mechanics. I'm going to go and take a break. There's ads coming in 15 seconds. So that's good timing. And maybe we'll move on to talking about some of the tectonic stuff. Or like the causes of tsunami in general. If anyone's got any more wave questions, please let me know when I come back. It will be a few moments. I might make another hot drink, so I might be a few minutes. But mommy. No, not again. It's fine. I'm fine. It's totally cool. I didn't clench. It's totally cool. I went up in my chair because I was excited, not because I clenched my buttocks. Okay.
Not because some poo came out.
No, that definitely didn't happen.
You are actually sitting on a mountain of diamonds right now.
Cool if that could happen. Don't think that's physically possible. Don't think the human buttocks are capable of that kind of pressure.
I mean, I've been accused of something today, Dodo, that's not my fault, but the person who accused me believes it wasn't my fault.
It's politics.
What? Because they're insane.
It was Sang, wasn't it?
No, it actually wasn't. Sang is eminently reasonable.
May I suggest you disclose your skills as a driver before you take on?
Well,
I've
never
felt safer.
End up going off-road.
Oh my. Let me take my grip.
You need to hold on to that oh shit handle.
That's quite the corner. I don't think that's a corner. Everyone okay?
Oh no! I'm high-centered.
How is this a naughty ship? Because it is one of the worst ships I have ever played. The fact that I have got, in the matches that I've played, the fact that I've got over 100k in half of them, and like less than 20k in the other half, speaks to the extreme randomness of this ship's damage output. Hi. Why is Lion bad? It's not bad, I just don't like it. Because in Lion and Conqueror, you have to be very, very... That was in Indianapolis, briefly. Guess how much health Indianapolis has? Okay. And anyway, continuing swiftly on. As I was saying, this is very good at deleting cruises, as perfectly demonstrated by that Indianapolis. because you have enough pen to pen and get citadels, but not enough pen to overpen because you're 356s, which makes it a perfect cruiser deleter, as perfectly demonstrated. Anyway, oh, that didn't kill you. Oh, that's annoying. That's very annoying. Do I wish I was secondary spec? No, not really. In this situation, main guns are still the king. Double kill? Alright. I am double bagging. I am double bagging in my pint mug. Got myself some lemon and ginger. This is a lot of talking. Did anyone have any more questions about, before we move on to sort of the more geological side of this? Did anyone have any questions about the wave stuff before we move on? Probably we've already covered stuff and I can like direct people back to a certain point in time. But I think we covered most stuff. Do I make waves or do I have definitely waves? Definitely waves. Rereading notes and essays. That's a good question. Do tsunamis have wave particle duality? No. So waves are waves, right? So waves behave like waves wherever they are. Whether they are waves in a fluid, waves in a solid. So sound waves, E waves coming from earthquakes, electromagnetic waves, they behave like waves. But the difference comes because of the medium that they're traveling in, right? So a water wave is a wave in water. An electromagnetic wave is a wave in a field, which is a very, very different thing. It's not really made of stuff like water is. And so while the wave aspect of it behaves the same way, the underlying material that it's a wave in is completely different. So no. If you do the double slit experiment, the famous electromagnetic waves experiment, you do that same experiment with water, you get the same thing, so you get the interference patterns, because the wave part of that physics is exactly the same. It's just the particle part of that physics is just not there because it's water. That's actually, I know you were joking, but that's actually a really good question. But you can, if you repeat the double slit with water, you will get the same thing. It doesn't matter what kind of wave you do this with, you get the same pattern. So you get this interference pattern, and this actually really, I should have showed this earlier when I was talking about the peaks and troughs and the interference. This is what I was talking about. These are those rogue waves, right? Southern Ocean rogue waves. You get like the waves coming off of one storm and the waves coming off of something else, and they're meeting at an angle. Wherever those waves have two troughs together, you get a peak. Wherever the waves have two troughs together, you get a big trough. They're wrong. Wherever you get two peaks adding, you you get a bigger peak, and wherever you get two troughs adding, you get a bigger trough. And then in between those, you get these slack areas where they cancel out, and the water height is the average water height, the same as it is out here. So this is what I was saying. And so these are how those rogue waves are formed. You get a really big peak meeting another really big peak, maybe another really big peak if it's three waves meeting together. Because you can imagine this source, and then maybe another source over here somewhere. You could have three peaks meeting together, which is not going to happen very often. Not going to be neat like this. Then you'd end up with a really big peak. So, if you don't know the double slit experiment, by the way, you're in for a brain-bending treat. Yeah, and here you can see it again, these interference patterns. So yeah, that's a good question. Yeah, I'm trying not to show anything copyrighted, Clarion. I feel very strongly about that. My position is slightly different when it comes to educational material. I don't quite have so much of a problem with people showing YouTube videos that aren't theirs and they don't have permission for education. But it's still copyright theft in theory. And so morally dubious, and so I try not to do it where possible. So I'm trying to explain things rather than show them. Right. Shall we talk about more of the geological side of it? Yeah, no, it's fine. I'm totally okay with, if people want to like share links to videos of things I'm talking about, go for it. I'm just not going to show them on the screen. That's fine. Don't have a problem. I would just rather avoid doing that. Okay. Think about sitting in a bath full of water, or being in a shallow swimming pool where you can like stand up. Think about the ways in which you could go about creating a wave. So there's a few different options. If you're trying to do it, let's say you're trying to do it with your hands, okay? You could do it by like jumping in, throwing an object. There's lots of different things you could do. Let's say you're trying to make waves with your hands. How would you do that? You can probably, I bet you can probably think of 3 different main ways that you could make a wave using your hands with the water. Just have a think for a second at how you would do that. So you're standing like chest deep in water, got your hands in front of you, and it's a very calm water, and you want to make waves that go out away from you. I think you could think of probably 3 movements that you could make. I'm not talking about like repeated movement. I'm just talking about like one motion. Keep it simpler. I think you have the options of some kind of lateral movement, probably a push, although technically you could pull. Just like put your hands together and just do that. You could put your hand below the water, so you could like cup your hands together like that to make like a table. And you can lift up. Okay, so if you put your hands just underneath the water and you lift, the water that's above your hands wants to flow off your hands, but it can't do that immediately because there's other water in the way. So as you lift, it pours off, and you temporarily create a little lump of water that then flows away. Okay. You could do the opposite. You could cup your hands under the surface water and pull down quickly. So you're creating essentially a vacuum above your hands. Water wants to flow in from the sides, and it pulls the surface of the water down for a little bit. The water rushes in from the side and then makes a little peak, and then the wave propagates. And so those are sort of the 3 basic ways of making a wave in that situation. You can push the water and make like a lump of water that travels away from you. You can pull down, create a dip that then fills in. You can push up and create a lump that then flows out. Sound waves are the same. Like I was saying before, all waves behave the same way. What is a sound wave? Do you know what a sound wave is? The same. If I click my fingers, what I'm doing is I'm suddenly moving my fingers, and that movement, especially the end, is suddenly moving the air around my fingers, and that air pushes on the air next to it, which pushes on the air next to it, which pushes on the air next to that. And it's the same as a water wave. So any wave in any fluid is going to behave the same way. When you get into solids, it gets a little bit different. And then when you get into electromagnetic waves, again, like I was saying earlier, it gets a little bit different again. But the basic behavior of the waves is the same. The way they propagate, the way they interfere, the way they cancel out, the way they go through slits, the way they go through small gaps, the way they propagate around corners. It's all the same. A wave is a wave is a wave is a wave. Yes, that's a very good point, Sam. Yeah. So, what sound? Oh, we can get really philosophical here. Sound, in the same way as color, this is an exact analogy. Sound does not exist. The what philosophers call qualia of sound that we think of as sound does not exist in any real sense. In the same way that the qualia, the quality thing that we think of as color, does not exist. It's just the way that our brains interpret that, in this case, pressure wave for sound. So when I click my fingers and that pressure wave in the air goes into my ear, moves my eardrum, and my ear detects that movement and translates it into electrical signals in my brain, I hear it as sound. That doesn't really exist, because what exists is that pressure wave. In the same way as color. What my eyes are seeing when I see color is I'm detecting different frequencies of light and translating it into color, but color doesn't really exist. Particularly, interestingly, in the visible spectrum, the color purple, my favorite color, the color purple, doesn't actually exist in a visible spectrum sense of the word. If you take a prism and you split white light into its constituent parts, and you look at all the different colors that come out, you will not see purple. There is no purple in a rainbow. If you don't believe me, go and look. Go and find pictures of rainbows and try and find purple. It's not there. I promise you it's not there. There are some colors that are kind of similar. Purple is the way that your brain deals with what happens when you get blue and red at the same time. It's like, no purple. That's essentially what your brain is doing. So yeah, it's important. It's important that you remember that what really exists in a physical sense, the thing that can interact with other things and transmit energy, is the wave. The pressure wave in the case of sound wave, the circular motion of the water in the case of an ocean wave, the oscillation, for want of a better word, in the electromagnetic field for a light wave or whatever. We've been all over the place. But how do we get onto that? I've completely forgotten. I've completely lost my track now. I love the the philosophy of qualia. So, you're red, blue, green colorblind. Holy crap. They don't exist, Doc. No, it's true. Sound waves. Oh yeah, because I was so quiet. Asked about sound waves. What was before that? Well, thank you, Dutch. Waves in 3 different ways, and then Quiet said is sound the same. So yes, there are. So we're going back to water now, specifically like the surface of the ocean. There are 3 different ways that you could suddenly get a wave going. So I'm not talking now about normal ocean waves. So what you're seeing animating on the screen here, which is ocean waves, like normal wind-blown ocean waves. Wind-blown ocean waves are caused by one fluid, air, flowing over another fluid, water. And the interaction between the air flowing over the surface of the water starts to pick up the water and create ripples, and they become waves. And the longer the wind blows and the harder it blows in the same direction, the bigger the waves get. That is not what I'm talking about. We're talking now about waves that are generated by something moving the water out of the way. So we're talking about surface of the earth moving. We're talking about bits of the earth breaking off and entering the water or moving underwater somehow. We're not talking about wind-blown waves. And so think again about the hands standing in the water. Displacement is a very good word. Pushing to create that lump of water that then travels away from you. Hands under the water, push up, and the water flows out. Hands under the water, pull down, creates a dip, and then that flows out. Interestingly, in that situation, just think about that for a second. So I have my hands under the water, and I pull down. The surface of the water comes down, so I'm creating a dip. Which way does the wave go? The wave goes away from me, right? So I do this, and the wave propagates outwards. But it starts by the water going inwards. So the wave propagation is separate from the movement of the water. If I do that, water flows in from here and goes whoop. But while that's happening, the actual wave is propagating in this direction. Because that trough that I create, then the water from here essentially falls into the gap, and that trough that I've created there then flows like that and flows away. And so going back to what I was saying earlier, like the wave is separate from the water. The water is the wave is in the water, but it's not the water moving. At least not over long distances. Are you still a gooey duck? What do we need you to be now? There isn't really there isn't really an applicable organism for what I'm about to describe, I'm afraid, because we're moving on to a completely different scale. Kraken, you could be a kraken. Go with kraken. Everyone can be a kraken. You right with that? Because then you can move around a bit. Is it the same as when you drop into water? Yeah, exactly the same. So obviously you're adding some material there, so you're adding some matrix. When you drop water in and it goes down, just like I was showing with the Chicxulub impactor earlier, that impactor has some momentum and it pulls the surrounding water down and then it goes back up again. Everyone's familiar with how that works, right? When you drop water into water and that wave propagates. But it's not the water that's moving out. Okay, so remember, the type of wave that we are talking about is created by the movement of something underneath it or next to it, right? My hands are now rock. The rock or material is moving laterally or moving vertically and displacing, great word, displacing the water next to it or above it. Okay. That's a beautiful kraken. So, what are, going to the geology side of things, the geomorphology side of things, what are the conditions, or some of the conditions, I can't go through everything, but what are some of the conditions that would result in some rock on some kind of big scale? So the scale of like towns up to countries, that kind of scale. On that kind of level, what kind of geological events can occur that would cause pushing or vertical movement? An iceberg breaking off is a great example. I wouldn't class that in the scale of events that could cause a tsunami, because that would be a pretty big iceberg. But yes, the event that you are referring to is called calving. And it's when the ice, which is at the edge of a glacier, which has flown down to the sea usually, or a lake, starts to float a little bit. And that motion, along with the melting and the pushing from behind of the ice, is actually my area of expertise, is glaciology. Bits break off the front, essentially. So you get these slices, because the ice is sort of extending as the pressure is released. You can see these cracks on the surface here. And so you get these literal vertical slices of ice falling off the front. And it's very dramatic. The ice obviously was above the water, and it becomes in the water. I'm sure most of you know, if you put ice in a drink, most of the ice is under the water. And so if the ice was above the water and it goes into the water, it pushes the water out of the way. We're going to get onto glaciology now, which is my area of expertise and my interest, and I'm gonna get sidetracked. Don't let me do that. But I have a really cool fact. So yes, this does create waves. And there's some footage, if you go looking, there's some footage of boats, lots of footage of boats, like tour boats, some science boats. Not so much with the science boats because they know what they're doing. But you see some like pleasure craft being in this situation here, on the water here. And on this scale, by the way, that piece of ice that's carving off there is probably quite big. A pleasure craft, like a tour yacht that you go, you know, on a little like 2-week pleasure cruise on, is probably on that scale, is probably going to be about that big. It's a big piece of ice. This carving piece of ice could cause a wave which could easily capsize a boat like that if you're close enough. So it's really important not to do that. Science vessels tend to be a bit bigger and a bit more resilient in terms of waves. But you'll notice that science vessels that are studying glaciers don't go too close. They just have really good optics. And it's very dangerous. So yes, this can create a wave. It's exactly the same process. It's just not on the correct scale to create a tsunami. But what can happen with glacial calving, which is really interesting, is you end up with this thing called a siege. And if anyone's been playing Dune recently, I think it's the same spelling, isn't it? Siege? Is that right? Is that how you spell it in Dune? I think it is. Oh, has it got a T in it? I was wondering if it was the same. So siege, different people pronounce it differently. What can happen is when you get calving events like this, it sets up a wave. So the ice drops into the water, a wave forms in front of it because of the displacement of the ice, and that wave propagates down the channel, and typically glaciers are forming in narrow channels. Oh god, I've gone onto glaciology now. I promise we'll get back to the tsunamis. If you go and look at, I'm rapidly coming to the conclusion that Google Maps is much better than Google Earth. Google Maps. So we're talking about like this kind of situation, right? Greenland. So you have these glaciers coming off the ice pack. So this is the ice sheet of Greenland. It's very, very thick. In places, this is more than 1 kilometer thick. Sometimes maybe 2 kilometers if you go up here. And at the edge, ice over a long period of time flows like water. And it flows down into these valleys at the coast that the ice itself has created. And then at the bottom, you get the edge of the glacier and it carves into the water. And that's exactly what you're looking at here. I wonder if anyone's taking pictures. Huh. Any photos? Any carving lovers? This is probably too far away. Look at it, stunning. Oh, I can tell. Oh. I'm gonna end up talking about moraines, and I don't want to. Okay. Yeah, no, let's not get distracted by the ice. Right. Okay. So this kind of situation, I think this one's probably a better example. So you have this glacier here, which is carving into this channel here. Under the right conditions, if this is a very clean glacier front that doesn't have a load of crap in the water in front of it, what can happen is that wave can propagate down these channels almost unimpeded, because some of these channels are very, very deep. And what can happen is if you end up with like a right angle like this, that wave can bounce backwards and forwards. And so it will come down here and like literally bounce off of this bank here, or this cliff, and some of it will turn this way, but some of it will go back. And so you end up with this siege situation, where you end up with these wave oscillations going backwards and forwards. And what's really interesting is if the length of the oscillation is multiple of the wavelength, the wave interferes with itself positively, because the peak, like the peak going this way meets the peak coming this way. And you can end up with these amazing, very, very rare wave interference patterns where you end up with these crazy waves as the wave interferes with itself, bouncing back the other way. This actually happened recently up here, which is why I'm showing this area. Some scientists saw some really weird wave activity, like, what the hell is that? And then they realized what it was. They realized that it was a massive carving event on the front of one of these glaciers that caused these waves and these oscillating wavefronts. So yes, going back to that comment, that situation can set up a wave, but it is orders of magnitude smaller than a tsunami. Wouldn't an island volcano blowing up? Yes, we will get to that. I think Jerry said the same thing. Yes. So ice, yes, can create waves. No, cannot create tsunami, because the amount of ice that you would need to carve off all at once in order to create a tsunami level event is just impossible, because you're talking about an area of ice like this, and it would need to be above the water and fall into the water. That's just not physically possible. And oh, I forgot my interesting fact. But areas of ice that big do fall off, in a sense. If you go down to like the Weddell area, like on Antarctica, there's these big ice sheets. They carve, and quite often in the news you hear about these country-sized pieces of ice that break off from the main ice sheet and float off into the ocean. Some of these things are enormous. But they can't create a wave because they're already in the ocean. All that happens is they just crack and start moving away. There's not like a big energetic event. They just separate and move off on their merry way. There's no massive transfer of energy. And so that's not going to create a wave. For the same reason, this is the interesting fact. So when you hear people say, hang on, let me just find a picture. Antarctic ice sheet break. Here we go. Here we go. A76, 4,320 square kilometers, approximately the same size as Mallorca. It's a big bit of ice. You could calculate the volume of that thing. You go and look up how thick it is. But that iceberg is already in the water. So these ice sheets, so the Ron ice shelf, for example, is forming in a bay of sea ice. This is ice that's already the ocean. And so there's this common misconception when people hear and listen to everything I'm about to say. When people hear, oh, there's these massive country-sized pieces of ice breaking off of the Antarctic ice shelf, we're all going to drown. It's not going to happen from that specific event because that ice is already in the water and ice displaces almost all of its volume. It's almost 1-to-1. So it's already in there. It's already displaced that water. And so if that iceberg carves, like A76 is doing here, and it moves north into the Southern Ocean and it melts, the ocean, the change in the global ocean is, for all intents and purposes, 0. Carving of ice sheets does not cause, carving and melting of ice sheets does not cause sea level rise. Will ice melting cause sea level rises? Yes, but not from that, because it's already in the water. The kind of ice melting that causes sea level rise is this. Ice that's above the water, sitting on land, that reaches the water and falls in. Because then the ice doesn't even have to melt. All the ice has to do is be in the water. That transfer from being in the air to being in the water is what causes the sea level rise. The ice melting does nothing. Right? Interesting fact. If you're equating Antarctic ice sheet breaking up to sea level rise, that's not correct. All right. So, let's try and get back on topic. Where were we? Okay. Ice, no. Rocks, yes. There are different situations in which sort of think of on the scale of towns to US states or countries, small countries, those kind of sized movements. So you're talking about things like tectonic plate movements. Very, very simple map of the tectonic plates from Wikipedia. As these plates move around and butt up against each other, some interesting dynamic things happen at the plate boundaries. And quite a lot of the time, those interactions can cause earthquakes and sudden rock movements. So all this stuff is all moving around all the time, just very, 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 very slowly. Of course, if two things that are very, very big and moving very, very slowly meet each other in some kind of way, simplest way being just head to head, then obviously they can't keep moving through each other. It's impossible. And so something has to happen. And the first thing that happens is pressure starts to build up. And so if you imagine two big blocks of rock meeting each other, pressure starts to build, and then eventually something has to give. And what's going to happen is at that boundary, one layer of rock is going to go down, the other one's going to go up, and it's going to do that. And then you end up with what's called a subduction zone on a large scale. And I just tried to rotate the Earth then. And the annoyingly off each side of this map Pacific Ocean is surrounded by almost entirely a subduction zone. This is what's called the Ring of Fire. And the Pacific Plate, which is very old, is being subducted underneath almost all of the plates that are around the edge of it. There's a few little areas here and there where it's not, but mostly it is. And you can actually see down here in the key, blue is subduction zone. So this is blue, 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 bit of messy in here, blue. So it's a lot of subduction. So that's one situation. I'm going to go into each of these in a bit more detail. Another situation, completely different. Because I just want to cover off, let me cover off like the basic categories and then we'll go into each one. So subduction zones. Extension zones, let me just cover the other end of this. So this extension zones, like the Mid-Atlantic Ridge, which is this red line here. All these red lines are all extension zones. These don't really do that. They do have earthquakes, but they're generally not as violent and there's not as much movement involved as subduction zones where they can be huge. And so these spreading centers, think of these as just gently bubbling and getting along with it and not really doing anything exciting. They don't cause tsunamis, really. Other type of plate boundary, essentially, is ones that do this. So, that way. Like the San Andreas Fault. Again, doesn't really lead to tsunami because most of the movement is lateral. And like going back to the bath, in order to get the water to form a lump, you need to move something either vertically or you need to push it with some kind of wall. And a fault underwater doing that is not going to do that because the water above it goes, eh. Nothing bothering me, I'm just going to stay still. And so the only plate boundary that really causes tsunami is a subduction zone. Another way that you can get vertical movement of material under the water is slippage of sediment. This is a huge topic, which is really interesting, and sedimentology is kind of my focus as a geologist, and so this is something that I'm really interested in. So going to an area of the world that I know. So you have rock exposed above the water. This happens to be the UK. And when rock is exposed above the water surface, it's subject to weathering. That rock gets ground down into smaller and smaller bits of rock and mud and sand and silt. And that's taken off of the land when it rains and by wind and dumped into the sea. And it forms mud and silt sediment on the bottom of the seafloor. But it's quite shallow here, right? Because this is still this is the bit that's sticking up, but this continent is, all the way out to here. I'm not going to go into why, but I could. This shallow sea, which like the North Sea, for example, is like 30 to 50 meters. It's not that deep. This used to be land as well, by the way. If you actually zoom in, you can actually see river valleys. I don't know if you can see it on the scale of this map. There are some maps that you can find of the seafloor bathymetry, and you can actually see paleo valleys that have rivers flowing through them. Over here, there used to be a landmass called Doggerland between the Netherlands and East Anglia that was populated. It was above land, people lived on it. It was actually the best land in the area. The lowland, the lush, rich lowland. And then at the end of the ice, then at the end of the current glacial maximum, we're still in an ice age. the sea level rose when the ice melted and inundated Doggerland, but it's still down there. And there's some efforts now to go and do some archaeology down there, which is very difficult because you have to do it underwater. Anyway, this this shallow seafloor gets covered in sediment. The sediment moves gradually into deeper and deeper water because on a slope, things are obviously going to be subject to gravity, and anytime they move, they're way more likely to move downslope than they are to move upslope. So sediment is always going to try and move downhill. And that means that because it's shallower here than it is out here, the sediment's going to gradually move out towards the deeper and deeper ocean until it gets to the continental slope, which is the thing. This is the boundary, the geological boundary, between the continental rock, the light continental rock which sits on top of the ocean crust, and the ocean crust. So this is ocean crust, this is continental crust. The continental crust sits on top of the ocean crust, so this actually goes underneath this. This sits on top like foam on a boiling stew. Can't think of an analogy. Like a cork floating on water. And this sediment starts to build up, right? So these are pretty steep cliffs. These are literally cliffs. They're the huge cliffs. These things can be kilometers high in some places in the world. And they look like cliffs that you'll be familiar with on land, right? So if you imagine, if we go to a very famous area of cliffs, once I remember where they are. Any cliff enjoyers down here? Yeah, here we go. The famous cliffs of Dover. So they look a bit like this under the water on a much, much bigger scale. So if you imagine the sediment up here on the seafloor, the continental seafloor, building up, so the sand is building and building and building and building, and then the continental slope drops down into the deep ocean. Occasionally, that sand is going to build up enough that it can actually fall. It can actually do like a landslide because it's coming from up here and it's ending up piling up, a bit like, you know, those coin machines at the fair. And if you go to like an arcade, like an old-fashioned arcade that has those drawers with the coins on them, and you put the coins in the top and they fall down and they fall onto the coins on the thing. It's exactly like that. The coins are building up and building up, and you can imagine if the shelf wasn't moving, if you put enough coins in the top, eventually the coins are just going to fall off just under their own, you know, pressure. That can happen. So you can get these little landslides under the water just caused by the sand just building up. But what really causes big movements is earthquakes. Because of course a lot of areas in the world are seismically active and experience regular earthquakes. And every continent is surrounded in some way by some kind of continental shelf. And so when you get these earthquakes happening around these margins, sometimes what can happen is big wedges of material, sand, silt, mud, rocks, that's sitting up on top of these cliffs, that's built up over centuries, millennia, can suddenly fail. The front edge will start flowing and the whole thing loses its cohesion, just like it would do on land. Same thing that causes landslips on land effectively causes them underwater as well. And the whole area just flows down out onto the abyssal plain. And in some places you can actually see, I can't think of any that I would be able to see on this kind of scale. In some places you can actually see the scars where these things happen. I'm not sure this is not high enough resolution. When that happens, so this is very, very interesting, and I can go into all the geology of like the rocks that you get from this, which are called grits and sands, and it's all very interesting. However, the bit we're interested in, if you imagine, this is not how this formed, but just imagine for a second that this area here was sand that's gone thump and fallen out here. Just think about that for a second. Go back to holding your hands under the water in the bath, right? Imagine a whole bank of sand, the size of like Ireland, suddenly slipping down. Suddenly slipping, I'm trying not to hit my microphone. Suddenly slipping down a slope. It's exactly the same as you holding your hands underneath that shallow seafloor, because the height of water above here is only like 50 meters. Okay? So you end up with this sudden movement of sediment, and I mean sudden, like minutes. And we're not talking like it's built up over thousands of years, but it can move in a few seconds. We're talking like 1 minute, 2 minutes, those kind of time periods. It's going to pull down on that water that's above it. Because suddenly you've got a huge depth of sand and potentially hundreds of kilometers across, maybe. The water can't instantaneously flow in to fill that gap. So it creates a dip. And it's that dip that becomes the tsunami. So it's the opposite of what we were just talking about, where you push and it creates a mound of water that then flows away. This is the opposite, but it has the same effect. Because it doesn't matter to the wave whether you start with the dip or whether you start with the peak, the wave still goes. And so you form this dip, water flows in, the dip flows outwards away in a circle, away from that origin point. Obviously, it can be a bit more complicated than that because it depends on the shape of the sediment that moves and how long that slip took to propagate from an origin point. It's a bit more messy than that, but basically, form a dip. Dip moves. Dip fills in. Dip moves out. So the second major way that tsunamis can form. So the first one was subduction zones, and we'll look at that in a bit more detail in a second. The second way they can form is sediment slippage underneath the water, driven by earthquakes. So earthquakes can form directly by the movement of the rock, can form tsunami. But an earthquake can actually also create tsunami because it just jiggles the ocean floor and sediment flows down slopes, and that pulls the water. It's not directly the rock moving. It can be sand and sediment moving. That's main method number 2. We'll come back to that. Main method number, although that's basically it for that one. Main method number 3 is volcanoes. So, topically at the moment, I can never remember where it is. Santorini. Topically at the moment, Santorini is being evacuated because it seems to be experiencing some activity. There's been a massive increase recently in earthquakes, which could be a sign that an eruption is brewing. Because if there's an earthquake around a volcano, that can only really mean one thing, and that's that magma is moving somewhere. So magma is very mobile. It can be a lot of volume, and it moves around, and it moves rock around, it melts rock, moves rock, pushes rock, and that can cause earthquakes. And yeah, you probably will have seen it in your newsfeed, absolutely. Yeah. So volcanoes, obviously a volcano that's like in the middle of the Andes is not going to cause a tsunami because it's nowhere near the ocean. But lots of volcanoes on Earth sit in the water or under the water. The whole of Hawaii is a volcano. It's formed as a volcano. This is also a volcano. You can actually, this is the remnants of the caldera from the old mountain that used to be there. That exploded, took the Minoan civilization with it. Everyone died, we think. And a new volcano, a new vent is forming here. This is new, relatively. And so this is still very much an active volcano. And the type of volcano this is, Silver, I will come back to that. The type of volcano that this is very violent. This can be explosive. The Minoans certainly found that out. And when you have an explosion underwater, that can move the water. When you have lots of material that is just next to the water, that suddenly goes into the water, does this sound familiar? I hope it does. That can push the water. And so there's a couple of things to do with volcanoes that can generate tsunami. One is a process called caldera collapse, which is where a magma chamber under a volcano is basically supporting the whole thing, the whole structure. For a sort of like what you would think of as a traditional volcano mountain. It could be much bigger than that. You end up with this area that's supported by magma. An eruption happens, all the magma comes out as ash and lava and leaves a gap. So this magma chamber empties and the whole volcano is like just teetering on the edge of this big gap, and that can fall in. The edges of the volcano literally just fall into the hole, and that movement of material, if it happens underwater, can you do the same thing that I described earlier, where you hold your hands under the water, pull down. That caldera collapse can cause that vacuum that pulls the water down, and then that generates a wave. Okay, so that generates like a trough first wave. You can also get the opposite happening in the sense of the wave creation, where you have material coming out of the volcano, hitting the water and displacing the water. So you end up with pyroclastic flows and things like that. So the volcano, think of like a traditional artistic rendition of a volcano erupting. All the material goes up in the air. A lot of that material falls straight back down again and hits the side of the volcano and scoots down the side of the volcano. Pyroclastic flow. That material, which is very, very heavy and traveling very, very fast, as well as being very, very hot, can hit the water in a situation like this, because if the volcano is sitting just above the water, that material is going to go up in the air, come down and hit the water. When an entire mountain explodes, goes up in the air, comes down again and hits the water's going to move out of the way. Also, what can happen is because the pyroclastic flow is at several hundred degrees Celsius, the water can turn to steam as well, almost immediately. And obviously when you turn water to steam, it can produce a lot of pressure. And that can add to some of this pushing action. And so you end up with this very hot material itself pushing water out of the way, creating some steam, which also further pushes the water. And that can also create a tsunami, although you're talking about a range of scales here. So the kind of tsunami that you're talking about for this is not the same kind of scale tsunami that you're talking about for the 8.8 that we just had in the last couple of weeks. It's a different scale. This is much smaller, much more local. This is the kind of tsunami that's going to be felt around the Greek islands, probably not much further than that. Mainly because this is kind of landlocked to a certain extent, because you've got all these narrow openings that the wave has to go through. But these islands will feel it, and the mainland will feel it. But it's not going to be traveling across an ocean. You'd have to have a pretty enormous eruption for that to happen. Yeah, so I think that those are the main causes I wanted to cover. The subduction zones, sediment slippage, and both the caldera collapse and material ejected from volcanoes. Would it amplify the wave? Yes. But you also have to remember that a lot of the energy would be lost in doing that on average. So yes, the wave as it goes through this gap, for example, it's going to be really messy because this seafloor is very, very lumpy. And so the wave is going to be really messed up by the fact this is so lumpy. So like the wave is not really going to arrive all at once because the deeper parts will go quicker, the shallower parts will go slower. And so it's going to be pretty messy when it arrives. But ignoring that, if it was a single neat wave that arrived all at once, yes, it's going to get channeled into this gap a little bit. But a lot of that energy is obviously just going to hit the island. And so what escapes through this gap is just like this portion of the wave, because this portion of the wave hits the island and dissipates into the land. What goes through this gap then spreads out. So the wave that goes through here would then go like whoop, 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 and get bigger and bigger and bigger from that point. And of course that dissipates the energy over a big area. And so when a wave spreads out from a center, the energy per degree, like the energy per degree of that wave circle, less and less and less and less as you go out, because the wave is getting bigger and bigger and bigger in terms of its circumference. So once a wave passes through the gap, then it's going to have much less energy. So if Crete didn't exist, then the wave is just going to go straight out down here and hit North Africa. But Crete does exist, and so a lot of Crete's going to swallow a lot of that energy. But the waves that come through here and the waves that come through here are going to spread out in these semicircles. They're going to hit Africa, but the energy that got absorbed by Crete has obviously been removed from that. Interestingly, going back to our earlier discussion, the waves going through this gap and the waves going through this gap are going to curve around here, and they're going to interfere with each other. And so this is essentially a Mediterranean two-slit experiment. And you're going to see interference patterns in the Mediterranean down here, potentially. But going back again to realism, the seafloor here is very, very lumpy, and that's going to affect the way the wave propagates. Okay. So, excuse me a second, I need to drink some. Double bagging. Let's go back to subduction zone. Trying to avoid as much drawing as possible. So going back to the first example, the first situation. So we're talking about subduction zones. So that is all of the blue lines that you can see on here. Interestingly, we were just talking about Crete. Crete, the reason that Greece is volcanic, the reason that the south of Italy is volcanic, is because the African plate, specifically the Nubian plate, is subducting underneath the Eurasian plate. This is a very small subduction zone, which is why it's volcanic. Whenever you see this situation, plate subducting underneath other plate, so here, the way around here, down here, what's along this edge of South America? Massive chain of volcanoes. What is here along this part of the Pacific Northwest? Massive chain of volcanoes. What are the Aleutian Islands? Massive chain of volcanoes. Same for Bali, Indonesia. You think about all these places on Earth where these blue lines are. They're all volcanoes. That situation. There. I can find a diagram rather than draw a diagram. This is going to save me a lot of drawing. Okay, let's start with this. So, I don't want to cover off the whole of plate tectonics. Interestingly, if you would like to learn about plate tectonics in more detail, I have a YouTube video on this topic that I made several years ago using Microsoft Flight Simulator. If you just go to my channel and search for plate tectonics, I think, there's like a 4-hour lecture, essentially, of me flying around pointing at different tectonic features. If you're interested. But very quickly, plate tectonics is caused by mantle convection. So the mantle is, so this is Earth. This is the crust. This is the outer core, which is liquid. This is the inner core, which is solid. The mantle is kind of goopy. It's solid, but it's solid in the same way that clay is solid or plasticine is solid. Particularly, the example that usually gets thrown out is silly putty. So the consistency of mantle material at the deeper parts of the mantle is approximately the same as silly putty. So if you take a blob of silly putty and you leave it on the table and you come back 24 hours later, it's my field of study. My field of work is streaming. It will spread out. So you come back the next day to a puddle, essentially, of silly putty. That's about the same viscosity, about the same speed of flow as mantle material, mantle rock. Is that my video, SDR? Thank you very much. If you want a tour of different bits of plate tectonics, go and watch that. Mantle convection, so the mantle flows very, very, very slowly. Silly putty is a non-Newtonian fluid. Mantle rock is not a non-Newtonian fluid. You hit silly putty really hard, it shatters. So mantle convection caused by hotspots. So the heat in the mantle is not uniform. And where there's a bit more heat energy, that causes the mantle to rise. The analogy, and actually you can set this up as an experiment, is boiling syrup. If you take a massive like cooking vessel, take like the biggest pot you can possibly imagine, exactly like a lava lamp. Imagine a big pot of like some thick syrup, like molasses, like something goopy, sugar syrup. And you put that over a nice even heat source, so a nice thick bottomed pan, or like put like a pizza stone underneath it, something like that, something to really get the heat nice and even. So the bottom of the pot is being heated nice and evenly. There's still going to be little variations in the heat. Random variations because of the material or how much heat is getting to certain bits of the pot. What that's going to do is some bits of that material, so the whole material is going to heat up, and the density, obviously, of material as it heats up is going to decrease because the molecules in it want to be further away from each other. So the density decreases when it's hotter. The less dense material in this liquid wants to rise to the surface because it wants to be up above the heavier material. The cooler material, which is more dense, wants to sink downwards. And so this sets up these convection cells. And what you see, if you do this with a pot of syrup, if the pot is big enough and your heat is even enough, you will see hexagonal cells. You will see a honeycomb pattern. It's really freaking cool. You will see a honeycomb pattern forming in the syrup. All these tessellating hexagons, where the center of the hexagon is rising up, spilling over, cooling down, and then falling down the walls of the hexagons. Okay. Hadley cells, yeah, it's not exactly the same as Hadley cells, but it's a similar concept, yeah. The physics driving it is the same. The shape is a bit different. So So this material is rising up along these ideally hexagonal cells. And so you end up with these lines of rising and falling material. So the whole mantle is churning. And as it rises and it gets to the top, and then obviously on either side it splits apart, that is pulling, if you can imagine like a river underneath ice, right? The river that's flowing under the ice is going to be pulling on the ice. It's going to be applying a lateral pressure to the ice, and that ice is going to want to move. You put a surfboard in a river, the surfboard doesn't stay still, it goes with the river. If you get in a river, you go with the river. Same thing happens to the crust. The crust is solid. It's floating on this semi-liquid thing called the mantle. The mantle is flowing. And whatever direction that mantle is flowing underneath the crust is tugging on that crust. And so that's going to pull the crust in that direction. And what happens is where the crust is being pulled apart, you end up with the crust. This diagram is actually wrong. Not quite right. You end up with a thinner crust. It does sort of show that, but it's not quite right. You end up with thinner crust at the ridge. The mantle material can actually, it's so thin, the mantle material can actually reach the surface. And you end up with a very, very geochemically complicated process where bits of the mantle material melt and bits of it don't. And you end up with what's called differentiation. Some of the minerals come to the surface, form basaltic magma, and that flows out over the surface at these ridge lines, and it forms new crust. This is how ocean crust forms. And then it's on the ride then. So this crust forms at the mid-ocean ridges, like classically the Atlantic ridge. So this is the Atlantic ridge. It's a spine type thing running down the middle of the Atlantic. This is the mid-ocean ridge. So that is, and magma is being solidified down this ridge the whole way down, and it's forming new oceanic crust, which is then on the conveyor belt. The conveyor belt is flowing this way towards Africa, and on this side of the ridge it's flowing this way towards North America. And then it's solid rock on a conveyor belt. So this solid rock sitting on the conveyor belt then travels across. So if we're looking north, like Iceland is up there somewhere. This is Africa. This is America, right? So not quite, because there's no subduction zone here, but that's actually a really bad example. This is the Pacific. This is some Pacific Ocean ridge somewhere. This is like New Zealand, and this is South America. That's a bad example. The solid rock is then traveling on top of this mantle conveyor belt until it reaches another continent. So in the case of the Pacific is very old, it's very complicated, but the same situation is basically there. The Pacific plate opened along one of these ridges, and then at the margins where you can see these blue lines, it's subducting underneath another plate. Same thing is happening here, same thing is happening all the way around here. And what happens when you get that situation, really low quality image, but oh well. This, for example, is the Juan de Fuca plate on the edge of the Pacific, subducting underneath the Pacific Northwest. This is the solid ocean crust that formed at the ridge. It's underwater. This is the mantle that's pulling it. So while this arrow shows the direction of movement, actually the pressure for that movement is coming from down here. This subducts underneath the North American plate, which is lighter because it's continental rock. This drags a whole bunch of water down with it, which is really, really important. Not to what we're talking about today with the tsunami, but for this process, the water is very important. The water helps the melting, essentially. So this wet rock dives down underneath this continental rock. It melts, and the differentiated magma which comes out of that travels up, because it's lighter, through the continental rock and appears at the surface, and you get Mount Hood, Mount St. Helens, whatever volcano you care to name in that area. They're explosive and horrible and cool and volcano-y. That's not the bit we're interested in. The bit we're interested in, I wonder if there's a... big. I wonder if there's an animation in here. It's a very texty article. Ooh, what's this? Ooh, that's cool. No, I might have to draw this. Okay. So, we have, let me redraw that image. So we have, I'm going to draw the continent first because I want to be able to undo. So we have the continent, which I'm going to draw in brown. I'm going to try and draw this a bit more accurately than the diagram you've just seen. And then underneath that, which I'm going to draw in dark red, is the ocean crust. So the continental crust sits on top of ocean crust, essentially. So there's sort of like a wedge down there of that crust as well. But that's not usually shown in these diagrams. And then you've got the pure ocean crust, which is coming along here and diving down underneath. I'm going to leave a gap. There is no gap. That's diving down underneath. It's going this way. And that looks like this. And then underneath that is the mantle. And the mantle, which is kind of goopy, is flowing that way. Cool. What happens is this is not a smooth process. It's rock. It's solid rock flowing past other solid rock. If you take two house bricks, and you put them together, and you try and slide them one past the other, I promise you it is not a smooth process. Now scale that up to the size of a continent. It's not a smooth process. It's very grippy. Yeah, it's high friction environment. And what's going to happen if you imagine sliding? I don't have any sandpaper. I could have had sandpaper with me. If you imagine two pieces of sandpaper, and you put them like sand side to sand side, and you start pushing one of them, it's going to pull that top one with it, right? So that top sheet of sandpaper is probably going to bend. There's going to come a point where this bending in that sheet of card is going to reach a point where it overcomes the friction. And so what starts to happen in this situation, this is extremely simplified, but it'll do. What can I use? Let's use green. So this area here, this whole area, starts to flex downwards. So you've got this rock layer going under here. This is very, very frictiony, and it starts to do this. Okay. So to simplify this, what you end up with is a situation which initially looks like that, and then it starts to look like that, and then it starts to look like that, okay, as this gets pulled further and further this way. All right. The continental crust is bending, but it doesn't want to do that. It wants to be flat. It used to be flat. It likes being flat, and it wants to flatten out. No, Sammy. The mountains, so along the Pacific Northwest, for example, along the coast of Peru and Chile, the mountains are not really formed like that. Not in the way that you're thinking, anyway. They're formed by the volcanoes. So the height of those, the peakiness of those mountains is volcanic, not tectonic. That material that you're seeing up there that forms the mountain is volcano material. There is some kind of crunching on a bigger scale. You do get mountain chains being formed this way. But the scale that I just want to make sure that the scale that you're thinking of, that material is formed via the volcanic action. So it's a buildup of lava and ash over time. Like the peaky part of the mountain range on the top. The icing on the top, if you like. The bulk of the mountain chain, the root of the mountain, yes, that is formed by this process. The Himalayas, exactly. And if the Himalayas go on, but the Himalayas, if you think about it, compared to, going off on a tangent again, but it doesn't matter. So so this mountain chain here is very kind of skinny. And a lot of this elevation up here is volcanic. The backbone that it sits on, the wider backbone, that's tectonic. And you can actually see the ridge here. It's really, really clear, right? You can see the subduction zone. Oh, look, ads. If only I had oh, wait, I have a YouTube channel. I wonder if that's still... Oh, it is. There's no ads over on YouTube. Just thought I'd mention, you know, that fact. Yeah, so this plate here is subducting underneath this plate here. This is the, this is that. And the pointy part of this mountain range is volcanic. The main flat structural backbone of the mountain is tectonic, caused by the rock crumpling. And if you go to a younger mountain chain, like the Himalayas, this is much, much younger. What do you not find here? Volcanoes. Yet. This hasn't quite reached that stage yet. So the beginning of a subduction is the rocks kind of going against each other until one of them wins, essentially. So the pressure builds and builds and builds and builds. And while that pressure is building and building and building and building, that's when you get that orogeny, great word, orogeny. I'll type it in chat. Orogeny. Good word. It means mountain building. Orogeny. The origin of mountains. As that land buckles in both directions, so it goes like that, right? Eventually one of the two pushing plates wins, and it subducts underneath. And that's when the volcanoes can start to form, because you've got this subducting, especially if there's an ocean involved. So you get this wet rock going down underneath and partial melting, and you end up with volcanoes. The Himalayas haven't reached that stage yet. So all of this orogeny here, all of this mountain building that's gone on up here, is all crumple zone. Like when two cars hit each other and, you know, the bonnet goes all zigzaggy. Exactly the same. It's the two plates buckling as they hit each other. But South America has gone a step further, and you can still see the buckling zone here. You can actually see that. You can actually see the waves going out from the buckling here. Like, it's amazing. And I cover that in my other video. But this has gone a step further, and you've got the ocean plate subducting down underneath this subduction zone. And then you get melting and the volcano. Very true, SPR. Yes, exactly. What's really interesting about that, to take another completely irrelevant to Tsunami side quest, It's a little bit more complicated than that, but yes, essentially that's true. What's really cool, the people who currently live in this part of Scotland and the people who now, completely coincidentally, live down in, can I show terrain a bit better? So live down in the Blue Mountains, for example. They didn't know this, obviously, when they moved, but they migrated. A lot of Scottish people emigrated to North America and ended up living in this area. A lot of the people that live here are Scottish immigrants, or descendants of Scottish immigrants. They moved, they didn't know this, they moved from these mountains to these mountains. They're the same mountains. They are literally the same mountains. And so it's a lot more complicated than that because there's been a lot of mountain building events since then. So it's a bit more messy than that, but essentially this is the same mountain chain. So this mountain chain here used to go up through here, but the land up here used to be connected to the land down here. And since, you know, humans have come around and civilization has grown, these two halves of this mountain chain have separated. And the Scottish people who live here, their descendants moved down here, not knowing that they were literally moving to the same mountains. And that is one of the coolest facts in geology that I know. Is this used to be the massive ridge of mountains that went down the middle of a continent called, is that Pangaea or Gondwana? I think that's Pangaea. One bit of this mountain chain used to go down the middle of Pangaea. The other one used to go down the middle of Gondwana, and I always forget which one's which. Yeah, it's really cool. Does the existence of volcanoes in the Caucasus imply that the Caucasus is older than the Himalayas? Not necessarily, no, because obviously the time it takes for that process to happen can be quite variable. I actually don't know. You could easily go and look that up. If you go and look up the timeline of the Himalayas, which is very young, and the timeline of the Caucasus, which is, I suspect, much older, you will be able to find out. But don't take the existence of volcanoes as a sign of age, because that's not necessarily the case, because it might take a much bigger area of orogeny, like the Himalayas is like the biggest area of mountain building on the planet by a long way. It might take this zone a lot longer to get to that volcanic stage than a much smaller one. So the subduction zone around here, for example, is tiny because it only goes from there to there. And that could potentially accelerate the time it takes to go through the different stages. But you could probably go and look that up pretty easily. Let's go and look up the age of the Caucasus. Yeah, it might have been Afghan. I remember. I'm a bit... My paleo continence is a bit fuzzy. Also, a lot of research has been done since I was a student, so I'm not really up to date on that. No, it's fine, SBR. The whole thing's been a tangent. We're supposed to be talking about waves. Where do we get to? Right. So. The subducting plate. I wish they had a better picture in here. The subducting plate pulls down on this. And it's like a spring. Pulls it down, and then occasionally that stress overcomes the friction on the plate boundary, and it springs back up again. Exactly the same kind of motion as if I have like a ball of paper. I don't have a ball of paper. It's exactly the same as me doing this. So, like, ball of paper comes down with my finger gradually, over centuries, millennia, and the pressure's building and building and building. My finger wants to be straight. It springs up. So, pressure that's built up over many, many, many years, long periods of time. Pressure on plate boundaries, tectonic plate boundaries, can take millennia to build up. And then the longer it takes to build up, the more energy's been put into it, the more energy there is when it releases. When that happens, when that flick happens, of course it's a sheet that's flicking. It's not just my finger, it's actually all my fingers along an entire mountain chain. So you're talking about, going back to, say, South America. You're talking about, so see this trench here? So this is the subduction trench here. You're talking about potentially that entire thing moving. So the ocean plate is subducting underneath South America. This coastline here, all the way down here, is getting tucked underneath. And some point along that fault line will reach the point where the friction can be overcome. That springs upwards and that propagates out from that point. And the whole thing potentially can go boink. Usually it's not the whole thing, usually it's just a small section. But it goes boink, and then if that's underwater, which it usually is, imagine this entire thing here, this entire sheet, which is hundreds of kilometers long, thousands of kilometers long, this thing here. Imagine this entire plate of rock, which is dipping down at an angle, going whoop over the course of a few seconds. Imagine what that would do, and it's moving potentially by many meters. 10 meters, 20 meters, maybe more. Imagine a sheet of rock that big suddenly lifting up underneath the water. Going back to the thing of being in the bath and having the water, you know, having your hands just under the water and then lifting up. Imagine that along the entire coast of South America. It's a boop. It's a bit of a boop. And so what that does is exactly what you're imagining. It lifts up this bulge of water that goes all the way along the coast. Can't go inland, of course, because there's a freaking mountain chain there. And so most of the energy is going to go out and across the Pacific, in this case. And so if you have that failure, if you have that slippage that happens along the coast of, say, Chile, it's going to propagate out in a fairly straight wave, probably. Out this way across the Pacific over towards the Pacific Islands, and then eventually over towards the coasts of New Zealand and Australia. But waves will go in semicircles, right? So it's also going to come out from here and go up the coast of North America. It's going to hit the Aleutian Islands, Japan, the Philippines. It's going to go the whole way down. It's going to hit the coast of South America, of Antarctica. It will even, believe it or not, wrap around to a certain extent the south end of South America and come up this way, because waves can do that. Middle Earth will be wiped out, yeah. So if the tension builds up for long enough, the movement can be quite large, and it can be over a very large area. And if the subducting, this is called the accretionary wedge, this part. It's all the detritus, basically, that comes off the ocean floor. Like, so, this is massively oversimplified. There's kind of, you end up with sediment that's here gets scraped off and it piles up here. Called the accretionary wedge. And so that's what this is. That's the thing that gets moved upwards. It's actually the plate underneath it is what's moving, but what's on top of that is the accretionary wedge. The accretionary wedge gets suddenly pushed upwards, and all of that water flows out because it has to move out of the way, and it can, so it does. And then that wave propagates out over the Pacific, and all the stuff we were talking about earlier to do with wave propagation and the speed and everything comes into play. Ah, I didn't subject you to the maths. We could do the wave speed maths. San Andreas is different. San Andreas is a different kind of fault, mostly. Messy. Nothing in geology is tidy. They're going to have some nice diagrams for me. Can I have a nice simple diagram? That'd be nice. Not really. Fine, I'll draw one. I just wanted like 2 stick drawings. So the San Andreas Fault, at a very simple level. So we're now looking top down. Is you got a sheet of rock. Well, that California. California is now a rectangle. And it's got a crack going through it. Like that. This is a map. And part of that, so this sheet of rock wants to move this way, this sheet of rock wants to move this way, so you end up with a slippage going that way and a slippage going that way. Looking top down. These 2 pieces of rock want to slide past each other horizontally. That can't really form a tsunami, not in the same way. If that suddenly moves and it's a big movement, it's a lot of rock, that significantly moves the sheet of rock with respect to the ocean that's next to it. It could create some waves, but it's not going to be on the same scale as a subduction zone slippage. Also, it's kind of on land, but not so much with the ocean. If one of these is underwater, under the ocean surface, and it moves, the ocean's not going to do much. So, because if you go back to the bath model, if I'm holding my hands under the bath and I move my hands upwards, the water makes a big movement. If I have my hands under the water and I do this, nothing happens. Oh, I was going to talk about Iceland. So Iceland is kind of unusual. And again, I cover this in my other video. I'm repeating a lot of what's in that other video. Iceland is not on a continent. Iceland is oceanic crust at the surface, which is very cool. Iceland is formed because there is a mid-ocean ridge, the Atlantic mid-ocean ridge, at the surface. And the reason it's at the surface is because there is also a hotspot underneath that point on the Earth's crust, which pushes that part of the crust up, which is how that part of the ocean, which is usually kilometers deep, is able to be at the surface. And so essentially what you're seeing is a seam on the Earth, a spreading seam that's being artificially pushed up a bit more by a hotspot underneath it. That entire thing, Iceland, the whole of Iceland, formed by mantle material melting, coming to the surface and forming ocean crust at the surface. So the whole thing has been formed by basalt volcanology. The earthquakes the volcanoes that you're seeing right now on Iceland, that's how the whole thing formed. gradually over millions of years. If we give the San Andreas, if we give it a retainer, just a few bits of wood, nail it down on one side, nail it down on the other side, do that the whole way down it, no problem, fine. Iceland is called Hawaii? No, it's a slightly different situation. No, not quite. So Iceland is a hotspot, but it's also on the mid-ocean ridge. So you can see here, it kind of gets a little bit messy as you go up towards the Arctic. But you see the mid-ocean ridge here, it actually continues up under here and goes through the middle of Iceland. And you can kind of see the end of it coming out the other end there. So Iceland is the combination of a mid-ocean ridge, is the separation between the plate on this side of the Atlantic and the plate on this side of the Atlantic, and a hotspot. So you have hotspot volcanology and mid-ocean ridge volcanology, both things going on together. Mid-ocean ridge volcanology is driven by magma generally welling up along that line, but it's happening especially powerfully and quickly in Iceland because there's also this magma plume, sorry, not magma, mantle plume, coming up through the mantle and coming to the surface at Iceland, or what is now Iceland. So it's a combination of two different things. Hawaii is just a hotspot. There is no mid-ocean ridge here. This is pure hotspot volcanology. And the reason this is a line and Iceland is a splodge is because here the plates are forming here and then moving away from that point. So Iceland is not moving relative to the mantle underneath it. Hawaii is a massive line. This is all Hawaii, essentially. To a geologist, this is all Hawaii. That's Hawaii, this is all Hawaii, that's Hawaii, this is Hawaii. This is still Hawaii. Hawaii going up here, this is Hawaii. Hawaii stops there. Like 2,000 kilometers long. And this is all caused by that hotspot in the mantle, being in the mantle, while the Pacific Ocean plate moves gradually over the top of it, actually in that direction. Yeah, it's a good question. We don't really know the answer to that. Yeah, the why does it turn like this? Like 120 degrees. Why does it do that? We don't know. It's presumably some kind of change in the plate boundaries of the Pacific, because the Pacific is subducting. The Pacific is a very old, dying ocean. So this ocean is closing. The Atlantic is a brand new ocean, which is only just opening. Eventually, the Atlantic will look like the Pacific. This is closing, and so it's subducting around most of its edge. And isn't really forming anymore, because the subduction, sorry, the mid-ocean ridge that used to be down the middle of the Pacific is not there anymore. It's been subducted. And so this ocean is just being eaten, basically. But the edges of this ocean will have subducted at different times. And so just like Bath, let me think of an example. If you take a small pond, a fish pond, take a fish pond, a big fish pond, and dump a whole bunch of surfboards in it, little boogie boards. You know those little rectangular boogie boards? Take a fish pond, throw a whole bunch of boogie boards in it, and then let the wind blow them around. Right? They're going to keep banging into each other. And some of them will kind of like jump up on top of some of the other ones if it's really windy. But they're going to do that at different times. And if you follow one particular boogie board, it's going to like dip down. If it is the boogie board that gets pushed down, it's going to get pushed down underneath other boogie boards at different times, and that's going to affect the way that it moves as pressure releases. And so maybe the Pacific started subducting in one place first, so it's forming, it forms, and then it starts subducting on this side. So suddenly, the pressure here is released, and the whole ocean starts to move this way. And there's still pressure down this edge, and it starts to subduct down a different edge, and it starts to move back in another direction. So probably what this is, although we don't know, that's like the theory as to why this happened. Exactly why this happened, we're not entirely sure. But probably this was caused by different subduction zones getting going at different times, which caused the plate to change direction. But look at the size of it. The entire Pacific Ocean just like turned left a bit. Pretty cool. The other thing that could be going on, either separately or in conjunction, is that the plume could have moved. It could be that the plume has started to travel as well. That might be an aspect as well. We don't think they do that, but that could also be going on. Tsunamis. Did we finish subduction zone tsunamis? I think we did. So the subduction zone tsunamis can happen anywhere around the world where there is a subduction zone. And water. So anywhere on this map that you see a blue line, which is a subduction zone, you can get that finger flicking action at the edge of the plate boundary. And that can cause one of these uplift tsunamis. And they're usually big. They're usually really bad. They're probably the worst ones. And because the Pacific is so old and it's subducting around so much of its edge, the earthquakes that form those tsunami can happen all the way around. I mean, you can literally see, I'm in space right now. And you can literally see from space the trench that goes all the way around the Pacific. Almost all the way around. It goes around here. It's a bit more discreet down here, but then it comes back down here. Going down into here. Like, you can see it all the way around. That's all subduction zone. And all of that length, all the way around, can have those, and does have those kind of earthquakes. And so if you look at a map of earthquakes, I'm going to be able to have some kind of timeline. Oh, look. Gee, I wonder why it's there. If you look at where these earthquakes are, even just this, what is this? This is the past 24 hours. This isn't even a long period of time. This is a day's data. What do you notice just on this really small sample? This is a tiny, tiny sample. What do you immediately notice? The red lines, by the way, are the plate boundaries. The earthquakes, with a few exceptions, are on the fault lines. Funny that. And then if you amplify, can I do like a timeline stretch or something here? New. I think I can. Maybe if we go to European Mediterranean, blah, 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 blah. If we look at a week's worth of data, this is only a week. Look at how well, if you got in your mind that picture of all the red lines, right? Look at it. It's so incredibly clear. 0 earthquakes out here. None. Because there's nothing going on. This is just ocean crust just happily trucking along on top of the mantle. No stresses. Just doing its thing. here is where all the exciting stuff happens, right? There might also not be monitoring stations, so if there's no data, it might not necessarily mean there's no earthquakes. But look at where they're all clustered. This is where the recent one was. Yeah, Dutch, absolutely. You know, it's the old paradigm of the century storm, right? It's the same kind of maths and statistics. People get caught out all the time, especially in things like civil engineering, insurance, by this concept of periodicity in geoscience. They will read somewhere that a river floods every 50 years. Or this river floods to this height every 10 years. Like, oh, it happened last year. It can't possibly happen this year. That's not how that works. So while there will be a periodicity to things like earthquakes and volcanic eruptions and those kind of things, storms, winds reaching certain speeds, it doesn't mean it can't happen back to back, because if you look at the data over a very long period of time, you can work out an average, a very accurate average. But there's going to be clusters. There's going to be clusters of periods where big earthquakes happen right next to each other. And there's going to be clusters where it's really, really quiet. And over a human lifetime, there's no statistical significance in that kind of data in one point. Because the geological timescale over which these things happen is huge. Mind-bogglingly long. So with lightning, interesting. So if you assume that lightning can strike equally everywhere, which of course it can't. If you get struck by, if you're standing at a spot and lightning strikes there, and then you like reset the system, what is the chance of it hitting there again compared to any other spot that you might pick anywhere? It's the same. It's like lottery wins. The chances of the same numbers coming up in two successive draws is the same as two completely different sets of numbers, assuming you pick the numbers. It's a statistical fallacy. Anyway. So we don't know, because we can't see, we don't know how much pressure is building up in these systems. And so it could be that a huge amount of pressure has been building up for literally millions of years, and then it slips a bit, and we see that as a huge, monumentally big earthquake, but it's only one little slip in a series of slips that if you sped it up would be like as this pressure releases over a few years or a few months, a few decades. But that what you got to remember is that on a geological timescale, that pressure has been building up for a very, 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 very long time, potentially. And so, yeah, you can see two big earthquakes, you know, 1 week and then the next week, or 1 month and the next month, or whatever. That can happen because, you know, pressure is released gradually, usually. That's why you get aftershocks. When a fault moves, it usually takes a little bit of time for it to settle down, because the act of it being released allows it to release even further, because it kind of unsticks everything, right? It's like lubricating it. Suddenly you've got this mobile surface where everything's like broken off and is loose, and it's mobilized groundwater. And it allows it to move further. And so then you get small movements after that until the whole system kind of settles down and the friction takes over again. And that's why you get usually one big quake followed by a bunch of aftershocks when it comes to fault movements. So, the subduction zone earthquakes that can spawn tsunamis by uplift can happen anywhere there's a subduction zone, particularly around the Pacific Ocean. And of course, because the ocean is a big, deep, flat ocean, tsunami can propagate a long, long way, and they can get easily from one side of the Pacific Ocean to the other. Hey, Carl. How do they know that, Dutch? Because it's relative. We don't know how much pressure is built up. That assumes that the pressure at the last big quake was released to the point of there being no pressure. That might not be the case. You don't know. When a fault slips, it's not necessarily slipping all the way into a no pressure position and then it starts to build up again. It might only have slipped partially. What they're surprised at probably is the fact that you can have such a huge amount of pressure building up in one place. It's not that the I think maybe you're slightly misunderstanding what they're saying. What they're probably thinking is there's a lot more energy here than we thought there was. Not it's impossible because every slip resets to 0, because that's not the case. Because faults is like dragging your fingers down a blackboard. Like if you look at it at a microscopic level, your fingers are like going tick 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 tick. Doesn't necessarily mean the pressure ever reaches 0. Hey, Toffel. Do your homework. Yeah. So this earthquake still has some questions. Some think it woke up a volcano. Others think the volcano is waking up and caused the quake. Both are possible. For the same reason that I was talking about earlier, I'll get onto this in a second. The same reason that earthquakes can trigger underwater landslides. The same thing can loosen up all sorts of things, right? Earthquakes can trigger underwater landslides. Earthquakes can trigger glacial surging, where suddenly a glacier starts moving really quickly. Instead of moving millimeters a day, it's moving meters per day. It's been jiggled. Jiggling does all sorts of things. Jiggling can cause sediments to behave like liquids. Particularly bad around Mexico City, for example, where liquefaction regularly buries buildings in dry sediment because it behaves like water. Jiggling can unplug volcanoes. His volcanic system is a bit like a zit, right? So it's a pocket of liquid with a shell of hard rock over the top. And there's going to be stresses in there, and that liquid is being pushed down on by the rock, the gravity. And so it's under a lot of pressure. It's literally like taking a balloon and squeezing it. Eventually, if the balloon has a way of making an exit, whatever it is inside the balloon is going to come out. If you take a donut that is filled with jam and you start to squash it, it's going to find a way out. And so that gravity pressure, along with the fact that the magma can work its way up through the rock, those two things come together and eventually that pressure relieves itself. That can be sped along a bit if you jiggle the mountain. Because any pressure that's building up that's not quite able to escape, if you jiggle it, it causes peaks and troughs in that pressure. And if one of those peaks overcomes friction, or manages to crack a rock, bang, and the thing's gone. And so earthquakes can absolutely trigger volcanoes. And volcanoes create their own earthquakes, right? So as the magma is moving around and the solid rock is being cracked by the moving magma, those earthquakes shake the mountain, and so essentially the volcano can shake itself into erupting, depending on what kind of volcano it is. Aftershocks are generally not bigger than the main Quakesilver. It can happen. But generally speaking, you're talking about a system where there's a big release of pressure that decreases a lot of friction for the reasons I was saying earlier. Just things have been loosened up a bit. And that allows, once things settle down into that first position, it gives you a much lower threshold of friction for other things to move. Could be, for example, that earthquakes don't generally happen along an entire fault at the same time. In fact, I would go as far as to say that can't happen. Usually it fails at one point and it spreads along the seam like a zip. What can happen is you get a big failure that goes zoop, and it stops because it hits a friction barrier. The whole thing's kind of been loosened up a little bit, and the pressure's changed because things have moved. And then that allows another little section of the same fault to unzip a little bit further. Just like, you know, if you pull a thread on a sweater, get a big chunk of material out, and then maybe it starts to unravel a little bit later because you've kind of weakened it. So aftershocks usually are smaller. So in this case, probably it's the massive earthquake causing the volcano, because it was so deep. But could be the other way around, because like you don't know. Like on a okay, so this is a little thought experiment that I love. Shall I wait until the ads are finished? Let's wait until the ads are finished, because it's a really interesting thought experiment that I love. I am gonna sound like Barry White tomorrow. Holy crap! Ad starting. Why? When? Thank you. When Twitch starts its own ads, it takes forever. If you press the button, it starts immediately. I've never understood this. Presumably, it's taking some time to find the worst possible ads for you to watch. Excuse me. Bum, 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 bum. I'm gonna have a Jakeman's. I've drunk my pint of ginger tea. Yeah, that's my last one. If I throw this over here, I'll remember to fill it up. That went nowhere near where I wanted it to go. You get a free subscription from Amazon Prime that can remove UBs. Hate UBs. Yeah, Viper, but if you press the button manually, usually it starts immediately. And so I'm like, as someone who's done a bit of programming, I'm like, what is it about you doing it yourself, Twitch? What are you doing differently that's taking the extra time? Why aren't you just triggering the same process? It must be doing something additional. I don't know. Maybe it does like more analysis, or I don't know. No idea. Because the sort of ad analytics on Twitch seems to be very, very simple. It doesn't seem to really do any kind of like, what does this person like? Just shows you random ads. trip over it, it is in the way, and it is see-through. So that is possible. Also, if I trip over that, I may well kill myself on the banister. So that bonus. Yeah. Oh, I could trip. Oh, I could trip and impale my brain on a jigsaw. Even better. Yeah. I could trip, take out 3 guitars, and impale myself on a jigsaw. Cool. What's my remedy for a crooked throat? So what I've just done, so drink a big pint of lemon and ginger. Lemon and ginger, avoid dairy. I really swear by these. They're very good. You didn't get an ad on YouTube, but you still had to sit while we went. Hey, Mikios. No, I could do another one of those TTS streams, because that was hilarious. I'm not doing any roleplay anytime soon, it's fine. Vocal zone? It does a bit, actually. Yeah. No, seriously, if you work with your voice, even if you like work in a call center, I recommend these. Not sponsored at all, of course, but these are very good. They come in 3 different flavors: blackcurrant, lemon and ginger, and original, which is basically asphalt. And they are very effective. Ricola. They also have the one I'm sucking right now is Jakeman's. It's all good. Can't go wrong. A steam machine, yeah. Technique has a lot to do with it as well. Right. Oh yeah, the little thought experiment. So, I love thinking about this. And it's important to apply this to situations, geological situations, which seem really big. Imagine, if you will, a pencil or pen. You can do this if you would like. If you'd like to follow along. Take some kind of pen or pencil, something that has a sharp point. Needle, chopstick, whatever. Make sure it can't balance. And imagine, you can't physically do this, but imagine putting that down completely vertically. So it's balancing on in the case of a ballpoint pen, is a ball, right? So it's balancing on a ball. What's going to happen? It's going to fall over. But let's say for a second, you got super duper lucky, and you actually managed to get it to balance on the ballpoint of the ballpoint pen. Or on the pin of, like, the head of the needle. We know it's not going to stay there. But what is actually required in terms of a force to make that perfectly balanced pen fall over? It's tiny, right? Like a gnat's fart is going to knock over this pen. Breathing a slight gust of wind, literally a mote of dust hitting it. And if you ignore like molecules and forces and stuff like that at the molecular level or the subatomic level, you idealize that system, like physicists tend to do. If you make it a theoretical exact point, it is mathematically possible to balance that. You have a perfectly flat surface and a perfectly uniform rod with a perfectly uniform point at the bottom. It's mathematically possible to balance that. But, and there it is, Dutch, in that theoretical situation, the amount of force that you need to push that pen one way or the other, or in any direction, is infinitely small. I've been thinking about this for years. You can apply this thinking to anything causal, anything that has causality, where A results in B, you can apply this to. Okay. Let's think of a more human situation. Going back to the tripping up, right? Trying to think of something that's not too horrendous. So, I go out drinking. And at the bar, I do exactly the same. I'm spending exactly the same amount of time drinking. I'm having the same conversations. I'm breathing in and out the same way. The only difference in these thought experiment situations is the percentage alcohol content of the drinks that I'm drinking. So in universe number 1, identical copy of me is drinking alcohol-free beer. Copy 2 is drinking like 3% beer. Copy 3 is drinking like 10% beer. The copy of me that's not drinking alcohol doesn't trip over the pot and kill himself on the jigsaw. The one that is drinking the pints of 10% specially crafted IPA beer, all other things being equal, trips over the pot when he gets home and knocks himself out and kills himself on the jigsaw. Okay? So are we happy with that setup? No alcohol, don't die. Actually, I've made this grim already. Alcohol, die. But if you think about it, there must be a point. There must be a point where if there was an infinite series of alcohol contents, there must be one copy of me that consumes one fewer alcohol molecules than the next guy. The guy who consumes N-1 alcohol molecules dies, and the next one does not die. Sorry, other way around. N-1 doesn't die, N dies. That infinitesimally small difference can cause a massive result. It's basically chaos theory. So the same thing can happen, right? Yeah, James, absolutely. You say off topic. How off topic? If it's anywhere in the sphere of earth science, probably going to be fine. So with any situation where one thing leads to another, force causes a movement, a chemical reaction starts and causes something to happen, whatever, there must be a tipping point. There has to be. Moral naturalism. Holy crap. Okay. This might not be the right place to talk about that, but that is really, really interesting. Can you, James, I'm going to need you to define it. Can you define it for me? It's a really interesting question. So, there has to be a natural tipping point that comes down to like molecules moving and tiny, tiny differences in force. And if you imagine in the situation of a tectonic plate building up pressure, you could have a situation where it's literally, because it's a point failure, right? So it's one point on that fault that fails and then it propagates. Just like a crack going through glass. It's the straw that breaks the camel's back. You could have a tiny little volcano on the surface that just kind of goes, boop. Just a tiny little, like a rock falls down, you know. A rock kind of goes, boop, and rolls down the side of the volcano. And that shockwave of the boulder rolling down the side of the volcano propagates through the earth, hits the this extreme pressure point in the fault, and causes the fault to rupture, because that's the tiny weeny little bit of pressure that manages to overcome that infinitesimally small boundary. That must be true. And so you got to get out of the thinking of this tiny little event over here couldn't possibly have caused this big event over here. Okay. Is it likely? No. Is it possible? Yes. And that's basically chaos theory. Morals being a physical law, that's an assumption. Morals being a physical law is you have to justify that first. And I think you would find that difficult. It's an interesting point, though. Morals can be a future testable prediction. Morals can be a future testable prediction. Yes, but whose morals? Because morals are a human construct. They are an emergent property of our brains, essentially. And our brains can be different from each other's. My brain is not the same as your brain. My morals are not the same as your morals. No, it's a really interesting. So James, this is for me, this is a super interesting topic. It has no relevance to what we're talking about right now, but it's super interesting. So you'd have to define what you mean by morals as well. Because morals are different for different people and different animals. Because different animals display different morals. So that's a very difficult one to define. Because morals are not universal. Morals are also, thankfully, constantly changing. Yep. Morality. I'm not sure if I want to do a whole stream on morality, but yeah, that's going to get deep. Right. So. James, I appreciate you. I very much appreciate you. Okay, so, no, it's fine, James. Totally fine. An interesting topic. If you want to pick that up with me, I'd be happy to talk to you about it. So, subduction zones cause earthquakes. Earthquakes at subduction zones, particularly where they are covered by ocean, can cause tsunami, which can propagate over the ocean in the ways that we described much earlier, and can span an entire ocean. They can take hours to travel across, but they will travel across. They don't lose much energy as they go across, and they can devastate the opposite coastline, despite the fact that it's hundreds or thousands of kilometers away. I think I basically finished talking about it, but the underwater sediment slip. So as I said earlier, that can be just spontaneous. So the sediment, like if you take sand and you pile it up, so dry sand. Sand is actually really interesting, where it has, depending on the type of sand, it actually has an angle that it will not exceed. So if you take dry sand and you pour it into a pile, I'm sure you can imagine that in your head, it will form a cone, assuming you pour it accurately, form a cone. And the angle of that slope can be very accurately mathematically defined by sediment models. Depending on the shape and size of the sand, grains, that will determine the slope. When you add water to sand, the water itself gets involved and you end up with cohesion between the water molecules, which can pull the sand grains together, and you can form vertical surfaces. This is how you can make sandcastles out of wet sand. You can't make them out of dry sand. However, dry sand in air, so dry sand is grains of sand, quartz grains mostly, in a fluid. The fluid just happens to be air instead of water. But if you put that sand underwater and it's completely submerged in, the ocean, so it's very wet, that property of the water holding the grains together, that disappears, because now the whole thing is swamped with fluid, and the sand grains behave similarly to the way they behave in air, and so they form maximum slopes. And so at the edge of continental shelves, like here off Shannon, you can end up with buildups of sand and silt that build up on the edge of the continent here, and they just naturally deform. It's not going to cause much of a problem. It's not going to be visible at the surface probably. It's just little bits and pieces just falling down, little slippages here and there, like a road slip at the side of a road. That kind of scale. That goes on all day. However, if you can end up with this bank of sand building up at the edge of that continental slope, earthquakes happen. So around the world, there are earthquakes happening very regularly. And the British Isles, for example, experience earthquakes, not because of any tectonics, really. That does happen occasionally, but not really. Most of the earthquakes happening in this part of Europe happen because of a process called isostatic readjustment, which is the mantle flowing back underneath the UK and Northern Europe in general, because it was squeezed out by the ice sheet in the last glacial maximum. So we were covered by an ice sheet, almost 2/3, 3/4 of the islands. And that ice was up to 2 kilometers thick, and it pushed down on the ground, very, very heavy, and pushed the mantle out from underneath this area of the continent. Pushed it out underneath southern Europe. Now the ice is gone. That mantle material is flowing back underneath the UK, and is moving within the UK. Oh, no worries, James. I'm a little bit reluctant to talk about that because I'm trying to get through some topics with this topic that I've kind of planned out. But that's really interesting. If you want to shoot me a DM, I'd be happy to talk about it. Midlands, no, London. Yeah, so isostatic readjustment is going on here. Mantle material is flowing north underneath essentially Scotland. And that flowing and lifting of the ground, lifting of the crust here, and the dropping of the crust here, causes little earthquakes because the whole thing is kind of flexing and it's kind of cracking, and it causes minor earthquakes. And that is happening, little faults, little cracks, all over this area. And so we get magnitude up to about 5 earthquakes in Northwest Europe caused by that process. And of course, they don't just happen on the land, or what is now the land. They can also happen out on the shelf. And when those kind of things happen out on the shelf, say there's like a fault here that moves a bit, and you end up with a 4 or 5 tremor, sand gets jiggled. And in the same way that if you build you make a bank of sand on a metal plate and you shake the plate, it's probably going to fall over. Same thing. It's stable until it's destabilized, and then it flows. Yeah, you can, Dutch. So because the reason for it is the reason a sediment behaves like a dry sediment and is kind of like sticky, in that it tends not to flow until a certain point and then suddenly it unsticks, is just friction, right? So the grains, especially if it's an angular sediment, the grains are very angular. This is why building sand is angular. And why Kitty's play sand is round grains. Because it's softer. Those grains are tessellate, so they literally lock into each other because they're crystals. But if you jiggle them around, they kind of bounce off each other and they untessellate. So not only are they freeing each other from themselves and allowing them to find new lower energy states, but also that jiggling allows any fluid that surrounds that sediment to flow in. Because by jiggling, some of the force of gravity is temporarily reversed because the grains jump up in the air, essentially. And, you know, a fluid is a fluid, and air will flow into a sediment when you do that, but so will water. And it causes them to behave in very similar ways. And so, yes, liquefaction will occur. That's entirely possible. What you end up with here, feels Batman, thank you for the follow. What you end up with in this situation, where you get these banks of sediment, you get an earthquake happens, and a huge wodge of this sediment will fall off the cliff, essentially, and flow down onto the abyssal plain. Very, very similar to any like roadside landslip that you've seen, just on a much, 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 much bigger scale. What that does, when that material moves, it has to be replaced by something. And the something is the water. So as it moves down the slope, this mass goes whoomp. It pulls the water surface down. That pulls water in from the sides. But that dip that you create when that material moves down, dip, that's the beginning of the wave. Because that dip is going to fill in, so the water is going to pour into that dip, but the dip is already there. The dip is moving. So the dip gets filled in, the dip moves away, and then you've got your wave propagating. But in this case, instead of like the subduction zone, the wave starting with a lump, because the water got pushed up, here the water is being pulled down first, because the material is moving down, pulls the water down. And so this wave doesn't start with an upward motion, this wave starts with a downward motion, but from that point it propagates the same way. It's just that the bit that arrives first, when it reaches land, the leading edge of that wave goes down first, whereas if it was caused by an upward movement, the leading edge of that wave goes up first. And you can actually see this when a tsunami hits a coastline. How the type of movement, the direction of movement that caused that wave in the first place will present itself. Because the front of the wave will either be a trough or a crest. Because the wave has to start somewhere. The wave has to go in a direction. And it'll either be bulging or sagging, essentially. So as that wave propagates out over the ocean, this kind of one will be trough first. And that's where you see that water drawing out from the coastline. So yeah, that's not particularly complicated. So you've got the spring action of the subduction zone, you've got the pulling, sucking action of the sediment slip. And then the third example that we mentioned was some kind of lateral movement, some kind of material entering the water from the land. Typically a pyroclastic flow of some kind. You have places like Crete, Krakatoa, these volcanic islands, but they have to be a specific type of volcano. So Hawaii is never going to do this. If it's an explosive kind of volcano, which form at subduction zones, then you can get these explosive eruptions which throw a whole bunch of material up in the air or explode laterally like Mount St. Helens. And if that material impacts the water, then that can cause a wave. It's not going to be the same kind of scale as the ones that I've been talking about so far, which can be huge. This is more localized, but it's still classed as a tsunami. It's just on the smaller end of the scale. And it's going to be more regional, whereas the kind of tsunamis I've been talking about before are more global. Ozamar, I don't know what you're referring to. So pyroclastic flows and that kind of lateral material movement from a volcano. And then the other one associated with volcanoes is the caldera collapse, where you have and Santorini is a fantastic example of a caldera. Because you can see the fragments of the old volcano. So this is the old volcano. I'm sort of tracing my mouse around what used to be the edge of the old mountain. But the middle is gone. Because the middle went up in the air. All of this material got ejected. So all of the huge magma chamber underneath and all of the solid rock on top of it was up into the air. That came back down again. You would have had pyroclastic flows. Those flows would have potentially caused localized tsunami, probably going out in certain directions. Then eventually, a bit later in the eruption, the magma chamber empties and the overlying material can collapse. The roof of the chamber collapses into the hole that's now there, the vacuum that's now there. And that falling material can pull down on the water above it if it's under the water. Or if, like Santorini, it's sort of at sea level, what can happen is that collapse happens and seawater rushes in. And of course it's meeting a very hot environment and it turns into steam. It's like taking a really, really hot pan that's dry and pouring water into it. You can end up with a steam explosion. And that can also cause a tsunami. One of the smaller islands in Hawaii broke in half 10,000 years ago. Oh, okay, so that's very similar to that. You misunderstood what I said. That's very similar to the situation I was talking about with the sediment slip. So sand isn't. I'm trying to keep this nice and simple. So the sand is not the only thing that can move. You can of course get lumps of like islands and stuff falling off. That can absolutely happen. Anything that falls down under the water is going to cause this suction effect. The fact that Hawaii had a lump fall off is not because it's a violent volcano, because it's not. Nothing to do with the volcanism. Because a lump fell off. Right? Do you see what I mean? Hawaii is not going to cause volcanism-related tsunami because it's not a violent volcano. This slow, sputtering, basaltic volcano. Doesn't cause explosions. But bits of it can fall off. No, it's like an underwater. So basically, Hawaii is a very tall seamount. So you've got vents at the surface. So Hawaii would have started like this. So this is the new island, which is underwater. So magma is coming to the surface here from a new vent and pouring out onto the ocean floor, and then gradually that builds up. And they can get quite tall. So the difference in altitude between top of the peaks of Hawaii and the ocean floor is huge. And so the cliffs surrounding seamounts like Hawaii can be very steep. And so if a piece of rock breaks off one of these cliffs, it's just going to roll down the slope. And sometimes those bits could be quite big. If there's some other geological processes going on there that have jointed that rock, then yeah, big bits can fall off. And anytime you drop a rock underwater, especially if it starts above the water, it's going to pull the water down. The bigger the piece of rock that falls, the bigger the suction. It doesn't have to be sediment. It could be a solid rock. It could be ice, like we covered earlier. Are there large fields of methane clathate? Yes. So I'll say again, anything that moves, any kind of like material, whatever it is, that moves underwater, moves the water. If it moves up, the water moves upwards and tries to get out of the way. If it moves downwards, the water gets pulled downwards and water tries to rush in to replace the gap. It doesn't matter what moves. It can be sediment, it can be rock, it can be a boat, a whale. It doesn't matter. It all causes waves. If a whale is sitting at the surface and it suddenly dives, it causes a wave. That explains Santorini with sound effects. I don't even remember the sound effects. Does flowing lava tend to pile more steeply underwater? Yeah, so because it cools, right? I'm not a volcanologist, but because it cools more quickly underwater, then yes. Especially the kind of lava that you get at Hawaii. So Hawaii's lava is basaltic. And basaltic lava, mafic lava, is very, very runny. It's very viscous. When it's flowing, it looks a lot like water, like muddy water, in terms of the way it moves. It can flow extremely fast. And if that comes out on the surface, then it flows over the surface like a river. Kind of rivery kind of speeds. But if it comes out under the water, then you get the stuff called pillow lavas. Oops, missed. Huh, wonder where that is. Oh, apparently it's Jordan, or someone called Jordan took the picture. Well, that's cool. There we go, that's pretty good. Yeah, pillow lava. So when you have vents under the water, because the water has much higher specific heat capacity than the air does, so how much heat energy can that mass hold on to? Water has very, very high ability to hold on to energy. So when lava is in the air, it doesn't transfer a lot of that heat to the air because the air doesn't have very much mass to hold it. But the water is very, very mobile, is in contact with the lava, and can take a huge amount of energy out of it very, very quickly. So just think about how much energy it takes to boil a pan of water. And when lava comes out underwater, in contact with the ocean, heat is transferred very, very quickly to the water, which is flowing, and so it moves away. either through convection or just because the sea is flowing. And it freezes, literally, I'm using that word intentionally, it freezes the outside of the lava surface. So you end up with this blob of lava coming out of a vent, surface freezes, but the inside is still liquid. But it's inside now the solid case and it can't escape. Sometimes the pressure from underneath, because the vent is obviously still venting, sometimes that will then like crack through the surface and you end up with this kind of structure where it will form a skin, the skin breaks, a bit more flows out and freezes, a bit more flows out and freezes. And you end up with these sort of like coral-like sausages. Sometimes if it's a more viscous lava, you end up with it freezing and then not flowing, which is where you end up with these kind of structures. More like pillows. And just because of the way it's freezing as it comes out, it's going to behave very differently to the way it is when it's in air. Frozen, but still very hot, although you would be surprised how quickly the seawater takes the energy away. This stuff freezes in a matter of seconds when it hits the water. Super, and of course, because the deeper it happens, the less inclined the water is to turn to steam as well, by the way. If this happens at the surface, the ocean like boils. So you'll see that in Hawaii, where the lava is just underneath the surface or is flowing down into the water. It produces a lot of steam. But if that happens really deep, the bottom of the Pacific, it can't boil because it's under a lot of pressure. And that can affect the dynamics as well. But in the air, where the lava is less inclined to freeze because it can't transfer its energy as easily, it will flow more because it stays liquid for longer, cools down more slowly. Whereas in water, it cools down very quickly, it forms a skin, and the whole thing cools down quickly. And so you would see, if you took two similar events, one that was on the land and one that was under the sea, and you compare the rock that results from that, you would see that the crystals in the pillar larvae are much smaller, if not indiscernible. You end up with obsidian, potentially. Compared to the crystals that form through the lava cooling on land, where it's cooled a lot more slowly, where the crystals are a bit bigger. And then if the lava forms underneath the ground, it's going to happen, then the crystals can get quite big. The latent heat of evaporation, that's on the edge of my knowledge of physics. I don't know how the lava interacts with the steam. You'd have to go and ask a volcanologist. Presumably because the steam is less dense and is already very, very hot, it's not going to take as much heat away from the rock as water would do, although the steam is also going to be moving much more quickly. So the steam might actually drive more water to move in and replace it. So it could actually speed up the cooling because it's just moving more water, essentially. Because then it's not just convection, it's actual gas moving. I think I've reached the end of tsunamis. What else did I have on my... So let's just go back through and check I've covered everything I wanted to go. The tectonic setting of the Pacific Rim, subduction zone earthquakes, volcanic eruptions, submarine landslides and slope failures, bits falling off Hawaii, meteorite impacts. We kind of touched on that, but I didn't really get into the tsunamis of that. Symmetry of the Pacific Ocean. Oh, we didn't get into the maths part, but I don't want to do that. Seafloor photography. We kind of did topography a little bit. Coastal geomorphology, we kind of covered a little bit. This is tsunami run-up and inundation patterns we didn't do. Sedimentary evidence of past tsunamis. This is really interesting. not something that I know a lot about, but I know that there is work going on, for example, in the Pacific Northwest, and also in the Severn Estuary that we looked at earlier. Researchers are taking cores of coastal sediments and river sediments in those environments. They're very similar environments. And what they're finding is that significant tsunami events in the Bristol Channel, for example, are happening every few hundred years. And these will be caused entirely by sediment slippage off the continental shelf. And so, significant development has basically grown up in this region since the last one. The last one was quite a long time ago, longer than the average. And since the last one happened, cities like Bristol and Avonmouth and Bath and Gloucester and Cheltenham and Cardiff and Newport have grown. And so last time a significant tsunami came up the Bristol Channel and inundated all this land here, all that was there really was little farmsteads. And so there weren't many people there to record it. The people who lived there would have been illiterate, because they would have been probably Anglo-Saxon. And so it's not really in the historical record. There are a few mentions of it in the Anglo-Saxon Chronicles, for example. And I think researchers have found that specific event in the sediment record. But we've built a lot of shit since then. There's a lot of stuff here now that wasn't there before. And so we are overdue, we talked about this earlier, but we are overdue, as the press would put it, for one of these events. And if that happens out here, it could cause a lot of damage, because a tsunami that hits the open coast here is going to be, you know, potentially damaging to fishing boats and anything that's down by the seaside. But this is such a long, sharply narrowing estuary that it's really going to focus that energy all the way up. The Severn bore happens every few weeks, and exactly the same thing would happen. It's a funnel. And so we know from the sediment record, because you can go and dig this stuff up, we know that these tsunamis that come from the Atlantic inundate a very large area in the Severn Valley every few centuries. And the same studies are going on in the Pacific Northwest, where they're doing exactly the same thing around Vancouver, up here, down into past Seattle, for the same kind of thing. Tsunamis caused by both the thing we talked about earlier with the subduction zones, but also sediment slip, going into the sounds around Pacific Northwest coast. And they found a lot of them. So these fjords here have regularly seen tsunami events. Just not in human memory. And eventually one will happen. And unfortunately, with the sediment slip type, there's very little warning, because that sediment slip, it's going to register on seismographs, but not in the same way that a earthquake does. Because it's a much more sort of diffuse rumbling, because it's the sound of that movement being transmitted through the rock rather than the rock moving. And so the warning is not going to be there, because if you're talking about a sediment slip from here, for example, if sediment falls off here and goes down there, it's not very far. That's like, what, 50 kilometers from there to the coast? A tsunami type wave can get from there to there very quickly. You're talking like 6 minutes from there to there. And so even if it does appear on seismographs, there's no reaction time. And you'd have to figure out what it was. How overdue? So, like we talked about this earlier. So this concept of periodicity when it comes to any kind of Earth event, floods, storms, earthquakes, volcanoes, like anything that happens periodically. Over a long enough period of time, you can work out what the average is. So you can work out what is the average arrival period of tsunami events going up the Bristol Channel. You can work that out. You can dig down into the record. You can find all the tsunami sediment layers and you can work out how much time was in between them. And you can come up with an average. Let's say you work out the average is 200 years. And the last one was 200 years ago. That does not mean that the next one is due right now. That's not how that works. It's just an average. The period will be noisy. If you go back and look at the data, you're going to get lumps of them coming together. You're going to get gaps where there's none of them, especially with this. If you think about what's causing this, it's slips of sediment down this slope, which can happen any way along this slope, and that's completely independent. So it could be that some slips off over here, and then the next day, some slips off down here. So you can get two 200-year tsunamis, one on Monday and one on Tuesday. If the Earth does that, because it can. What you can't get, if you think about the mechanics, is something like, for example, 2 century storms, one on Monday and one on Tuesday, because obviously you can't have 2 storms that close together. So there are certain limiting factors depending on what the event is you're talking about. But the same kind of statistical truths apply. It is entirely possible that 2 different storms that come off the Atlantic 1 week after the next can both be century storms. The chances are very, 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 very small, but it can happen. And so if you have like a huge hurricane that comes in off the Atlantic and devastates the east coast of the States, doesn't mean that the very next one can't be the same. It's not likely to be, but it can be. It's very important to understand that. So this idea of we're overdue, like another one that's very long period, is Yellowstone. So I wonder if I can pick it out without looking up where it is. So not the Yellowstone itself, but the old calderas. So no, let's look up a map. Yellowstone his yeah. So that's the one I want. That's even better. Yellowstone's overdue. Not how it works. So you can work out how often Yellowstone eruptions happen. Again, we have a very good geological record of this, so we can work that out pretty well. If you look at the data, you're not looking at that many events, and so the statistical significance of that data is quite bad. And you can see there, like if you imagine that caldera is moving at the same speed, like you can see, like the sizes of these are different, the spaces are different. You look at the timelines, like the gaps between them are different. And it's like on a geological timescale, this is like a pendulum swinging, but it's swinging really badly. It's not like tick, 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 tick. It's kind of like tick, 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 tick. Like it's not regular. It's sort of regular, but it's not regular. Certainly not on a human timescale. So if you look at these dates, for example, with Yellowstone, you look through those, you get the kind of 2 million years. Let's just say 2 million years. Let's say the average period of these big super eruptions is 2 million years. And the last one was 2 million years ago. Is it more likely you pick the year 2025 and you pick a year a million years before 2025, 2025 minus a million, whatever that works out to be? Is it more likely to happen this year than a million years ago? Yes, because we can see that building pressure, caldera, black period, and so on. You can't say it's more likely to happen this year than last year, because on the scale of millions of years, 1 year to the next is nothing. It's just noise. So all we can really do with Yellowstone is try and monitor it as closely as possible, and rather than trying to use the periodicity of the caldera in the geological record, look at what's actually happening in front of our eyes. Try and understand what are the signs that precede a super eruption of a caldera of that size, and look out for them. Because that has nothing to do with this periodicity. Because people get too hooked up on, oh, it's overdue. On a geological timescale, that means nothing. Because human timescales and geological timescales are completely different. So 16 million years from the first one. The first one here, so this is the same as Hawaii, by the way. So in terms of the reason it's moving. So in Hawaii, the islands are forming in a chain because the Pacific plate is moving over the top of the plume. Here, it's the continent doing that, but it's the same idea. So the plume is staying still, and America is moving over the plume. The oldest one, 16 million years. But these are all eruptions. These are all calderas which have formed on the surface. 16.1, 13 to 15, 10 to 12, 7 to 10. Interesting, 7 to 10. 4.3 to 6.4, 0.6 to 2.1. So at some point, you go and look at, where are we here? I can never find it on the actual satellite view. So the top corner of Idaho. So currently it's in here. And you can actually see some of those calderas, right? So yeah. You get your eye in at certain times of the year, certainly with satellite images, you can see them. So the caldera is, from the point of view of America, traveling this way. And so 16 million years ago it was down here. If everything stays moving in the same direction, in 16 million years' time, it's going to be up here. So if you own property in Sumatra, Montana, you have about 16 million years to sell up and move. But it's going to have an amazing tourist industry. Yeah, so that's moving. So this caldera will, you know, erupt at some point, and the plume, which is sort of walking, right? So it's sort of doing this. Eventually, this plume vent will expire because it's moved on, and a new vent will form, and that's the next caldera. And the periodicity of that happening is very approximately 2 million years. And that will, if everything stays the same, that will keep happening. North America will keep moving. because the Pacific plate is, don't forget, the Pacific plate is subducting underneath North America. It's a bit more complicated than that, but just stick with that. North America is subducting under the Pacific, and so they're moving together, relatively speaking. And so North America is moving to the left on this image. And so anything that's underneath in the mantle that's stationary, you're going to see that move to the right, to the east. And that's exactly what's happening. Right. Alright, we finished tsunamis a long time ago. Anyone got any questions? Oh, it's a shame James isn't still here. We could have talked about morality. Anyone got any geology kind of questions? Earth science questions? Or tsunami questions? If you still have tsunami questions, I'm happy to answer. I just want to point out, I am streaming this live on Twitch and YouTube. And obviously it's much easier to scrub through a VOD and find a VOD on YouTube than it is on Twitch. So if you have come in partway through this and you want to go back and watch the beginning, it's on YouTube. The stream on YouTube, the VOD will be called Live on Twitch, Tsunami Q&A, Geology, Geomorphology, and Ocean Science, and you should just see it in my live VODs. We can still talk about morality? We can if you want to. James will be sad that he's missing it, though. Only the one you DM'd about Los Palma falling off. Yeah, so that's related to what I was talking about in terms of if anything moves underwater, right? So, and I kind of covered this when I was talking about Hawaii, but it's exactly the same situation. So if you have something like the Cabo Verde Islands, which are volcanic, Funchal, Santa Cruz, all these places are volcanic. And so, like Hawaii, they build up very, very steep slopes. And steep slopes don't like being steep slopes because gravity exists. Gravity likes flat things. If you leave rocks alone long enough, they like to become flat. And so bits fall off. So these get very, very tall. And the freezing factor that we talked about earlier with the lava freezing adds to the height underwater. And these things get very, very tall and stuff can slip off them. And so these slopes can fail. They get steep enough. And there's a weakness. And so yeah, if a bit of one of these islands falls off, it's going to create a big wave, and that's going to propagate over the ocean, just like we talked about. And could potentially be very big if it's a very big failure, particularly if there's some faulting associated. So something like Hawaii, for example, is pretty stable because there's not much tectonics going on. But if you have one of these kind of situations where there's a lot of tectonics going on, like around Greece, then you can end up with fault failure slippages, where it's actually a fault that's causing the weakness. And those movements could be quite big. I wouldn't expect sort of a chunk of island falling off to cause a huge tsunami. But if there's a fault involved, it could be quite big. Sammy, why do you think this last big tsunami didn't hit the US West Coast and Hawaii harder? So there's a few things to consider when you're thinking about the propagation of a tsunami, or any waves in general. The magnitude of the earthquake is related to the size of the wave, the amount of energy going into the wave. But you also have to remember the geological context. So this earthquake was very, very, very deep, as I understand it. I actually haven't looked into this particular one in huge detail, but I understand it was very deep. And the closer to the surface something like that happens, if you have an 8.8 that happens and the failure happens much, much closer to the surface, then obviously that energy is going to be a lot more concentrated at that point on the surface. If you go deep, that energy has to radiate out from that point under the ground. And we're talking like tens of kilometers down, maybe hundreds of kilometers down. That energy travels out through the crust, And so by the time it reaches the surface, by the time that movement energy reaches the surface, it's had to spread out quite a lot. And so although the earthquake itself was just gigantic, one of the biggest earthquakes we've ever seen, because it was so deep, that energy has partially dissipated by the time it reached the surface compared to an 8.8 nearer the surface. So that's part of it. It's part of the energy is very deep. The other thing you need to consider is once the wave forms, and I assume that the movement, again, I haven't looked into this specific example, but I'm assuming that what happened was the accretionary wedge popped upwards and it pushed a lump of water out of the way like we described earlier. Just starting from the other end of the Pacific. Once a tsunami forms, it travels out over the ocean. But tsunamis are so big that they actually do touch the bottom of the ocean, even though it's 4 or 5 kilometers deep in places, maybe more. And that affects the dynamics of the wave. The deeper the water, the faster the wave. And there's actually, I've spared everyone until this moment, but maybe I should show you the wave equation for the speed. So it is square root of GD. So if you take, can I do text? I can do text. Oh, I can't do square root. Let's draw it. Draw the maths. So I get back to pen, from pen. File, new. Don't save. The speed, the velocity of the wave, v, equals the square root of g times d. Really simple. How fast it goes is gravity, because gravity is what's called the resolving force of a wave in the ocean. So gravity is, anyone know? On average, on Earth, the surface. Anyone know? Pop quiz. 9.81 reckless round. Good job. 9.81 meters per second squared. I'm not going to put the units, you can imagine them. The depth is the depth in meters, in this case. So this would be, I'm going to write it as kilometers, but imagine it as meters, so it's the same units. So in this case, it would be approximately 4 kilometers for the Pacific. And if you I promise you, if you multiply those things together with the equivalent units of meters and meters, you get a velocity, and we talked about it earlier, with tsunami propagating at the same speed roughly as a passenger jet plane. That's what falls out of this equation, like 400 kilometers an hour, something like that. But the shallower this is, the slower the wave goes. Okay? As the ocean becomes shallower, like I was talking about earlier, the wave kind of trips up over itself and it loses some of its speed, and that's when they get dangerous. That's when they become, instead of being this almost imperceptible dome of water, they become these waves. They become like a surging, pushing front of water. Because the back catches up to the front, the bottom trips over itself, and you end up with this horizontal surge. So, going back to maps. The Pacific is deep, but it's not uniformly deep. And so a wave going from, so the wave formed on the front of the slope here, a wave going directly south from here is pretty much unimpinged as it goes south here, so it's going to go as fast as it can physically go at that depth. It's going to be like 500 kilometers an hour. But then it's going to start hitting things. So it's going to start hitting what used to be Hawaii. It's going to start hitting this chain here. And as it does that, it's like you trying to jump over a fence, hitting the fence and falling on your face, right? Same thing. So the depth here is maybe only 2 kilometers instead of 4 kilometers. And so as the wave travels over here, and bear in mind that's not hitting it at 90 degrees, as the wavefront starts to hit here, it's going to slow down and dissipate some of its energy because it's going to start moving sediment and stuff around on the seafloor here. And because it's hitting at an angle, that's going to happen down the wave gradually over the course of several hours. And that's going to disrupt how the wave behaves as it comes out the other side. It's going to have lost a lot of energy. And so that's why when you go and look up the measured wave heights from this event at different places around the Pacific, even though they're like roughly the same distance away, some of these Pacific islands, so like down here in Hawaii, you'll see they get quite drastically different wave heights because it depends which bit of the wave and what the wave's gone over. Because if you get, for example, if you get a wave that's formed up here somewhere, the part of that travels directly south is traveling all the way along this chain. And so if you're here, so let's pretend there was an island here above the water. The wave that's traveled all the way down this chain has lost a lot of energy and has slowed down quite significantly. And the wave that's traveling here is going to be traveling much faster. And so what's going to happen is this wave is going to be sort of like breaking around the slower part of the wave, because this part's going to be going really slowly. This part's going a bit faster. And it's kind of going to like tuck in on itself. And that process is very messy and very turbulent. And it spreads the energy of that wave out. And so if the source was here and you are here, potentially you're not going to get a very big tsunami hitting you because it's been all messy on the way. Whereas if you're over here and the source is here, there's nothing in between you and that. And it's going to hit you like a truck. It's going to be much faster and it's going to have much more energy. That's why. It depends the path, because the ocean is not a uniform basin. It's got all sorts of lumps and ridges and bumps and channels. And especially as you start to approach the coast, especially in some parts of the world, you end up with all these little channels and dips and gullies and cliffs that all affect how the wave behaves once it reaches the shore. And so, like, for example, here around San Francisco, did I say it like that? Around San Francisco, you've got this shelf that goes out. So you've got the continental shelf that goes out from the coast to here, and then you've got the slope. But here, around Monterey, you've got these huge, amazing canyons that go all the way up to the coast, like literally to the coast. Like you could swim to that pretty much. It's not that far. Certainly you can get there in a little boat, right? And so any wave that comes from this direction and hits this part of the coast, or this part of the coast around San Francisco Bay, is going to behave very differently to a wave that hits Monterey. Because here, it's going to trip up over itself out here, because it starts to hit that shallow seafloor. And it's going to lose a lot of energy. It's going to start moving sediments. It's going to get more spread out. And so the wave that hits San Francisco could still be very devastating. But that surge is going to be more laterally spread out. It's going to arrive over a longer period of time. And it's going to carry less energy overall. Whereas Monterey, the wave pretty much just marches up to the front door and kicks it in. Because it's not losing any energy. And also, the slope of this sort of cone-shaped bay is going to funnel that energy inwards as the water tries to mount up onto here, but the path of least resistance is to go along. And so that wave energy is going to get funneled into here, and potentially you are... if you're this place... What is this? What are you? Some kind of... I don't know what you are. Scrap? metal something. Prices on fishing equipment. It's a fishing equipment shop. Steve, who owns the yard at Moss Landing and sells fishing equipment, is screwed. Compared to someone who maybe lives up in San Francisco Bay, where they've got the protection of that extra distance between them and the tsunami. And Fukushima, if you go and look at Fukushima Bay, it's up here somewhere. Not exactly sure where. Fukushima. I can't remember where the plant is. Does anyone know? Is it here? Is that it? I'm not sure where it is. Actually, I'm not seeing on the coastline what I was expecting to see. I think this was just like, it just hit the coast. But like here, for example, so you've got this big headland leading down into this bay. This is going to be a bit of a focus. If a wave comes from up here, that's going to be a bit of a focus. Obviously, if the wave comes from around here, it's not so much of a problem. Steve's lease payments should be super cheap. Yep. So yeah, the severity of the waves, the energy those waves carry, is going to depend on the path that wave has taken, and it can be very different. Like I was saying here, the source is here. The wave here could be very, very different to just, you know, a few hundred kilometers away over here. Very, very different, because there's been no interference. Any other questions? It's a bit south. Yeah, it's a fairly flat coastline though. The thing that Japan gets from there's a wave that's generated on the peninsula here or over in the Aleutians. It's going to arrive at, well, on the lower part of Japan, it's going to arrive at quite a steep angle. And so the wave isn't coming like directly on shore, it's sort of rolling down the coast, which makes it a quite different interaction. Because it's going to, you know, going to arrive here and then sort of go duk, 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 all the way down. Push things longshore. So, most important thing, if you're on holiday or you live by the sea, if the lump arrives first, you kind of hosed. If the trough arrives first and you suddenly see all the water drain away from the beach over the course of a few minutes to like half an hour, because this message and this knowledge has saved lives many times in the last century or so. You are at the coast and you see the water draining away from the beach, especially if it doesn't normally do that at low tide, or you know it's not low tide. Get as far inland and as far high up as you can as quickly as possible. If you can, grab some water, grab some food, but the main thing is get inland and get altitude. Walk if you have to, but don't stay at the beach. Especially, don't go, oh look, seashells. That fact has saved lives. Unfortunately, not many lives, but it has saved lives. These days, with early warning systems, hopefully no one will ever have to do that again, but because they'll know about it in advance anyway. But if the warning systems fail, or like you didn't hear the warnings and you're at the beach and the beach drains and you can see funky rocks that you shouldn't be able to see, leave immediately. Run for the Danish Highlands. Well, so interesting point, right? So these tsunami, going back to someone asking about Doggerland, there's a hypothesis that Doggerland, which used to be here, still is there in theory, just in the water. Doggerland was inundated when the ice sheets from the last glacial maximum melted and sea level rose. This was the lowlands. But there's a hypothesis that the final inundation of Doggerland, the last bits of the lumpy high bits of Doggerland, happened because of one of these sediment slip tsunamis that happened up here. So oceanographers, oceanic geologists have found scars. So when you have a slip that happens on one of these slopes, it leaves what's called a scar. So you can literally see it, and you can date those. And there are scars. I think that is one, actually, a massive one. It might be this one they're talking about. I don't know. I don't know this case very well. But yeah, they've found a scar which seems to date approximately, roughly, to the same kind of time period ago as the inundation of Doggerland. And so there's this theory, or hypothesis, that the final inundation of Doggerland, which was here, was from a tsunami. But the same thing can happen, of course. So if that same thing happens with up here, not so much down here because then it has to squeeze through here, but if something happens up here, off the Faroe Islands or off the Shetlands, a tsunami could easily propagate down through the North Sea, although the North Sea is very shallow, and hit the coast of the Netherlands in just the same way that it can go up the Bristol Channel. How do they date them? I'm not an expert on how they would do that. They will use things like how much marine life do they see? So one of the techniques universally in geology, above water as well as underneath water, and how old something is how much stuff is growing on it. So if you see a landslip by the side of the road, so you're driving along and you notice that some mud has moved, you'll notice that the surface that's left behind, and to a lesser extent the material itself that has moved, is like clean. And so that surface that's been left behind by the material moving is just clean. There's no biology there at all. At least not macrobiology. But if that slope is left alone, gradually, if it's something that's not vertical, it will start to develop like lichens and mosses, and then some soil will form, and then weeds come along and they die and they create more soil. And gradually that slope's going to get populated by plants, which are going to stabilize it as well. And so if you see one of those kind of like landslip slopes with a pile of rubble at the bottom, and that landslip slope has got trees growing in it, then it's probably not that fresh, right? It's probably decades old if they're small trees. If you see the slip slope and it's got, a little bit of lichen here and there and a couple of bits of moss and like a, dandelion, it might be a bit younger. And if it's completely clean, then it's just happened. You can do the same thing underwater. So you can look at that fresh surface that's left behind from the sand slipping off. And you can go and like count bivalves. So you can do a survey. Let's say you find a bit where you're pretty certain there hasn't been a recent slippage. So you survey here and you take samples and you work out, you dive down maybe, take a submersible, and you work out a grid pattern and you work out what's the density of mollusks in this grid square. And then you do that for a whole grid. And And then you do the same thing on the slip surface, and you can work out how many mollusks there are per square meter or whatever. And then the critical thing is that's going to tell you relatively, okay, well, there's no mollusks over here and there's lots of mollusks over there. So probably the place with the no mollusks is going to be younger than the place with the lots of mollusks. But if you can work out how quickly mollusks repopulate a new area, then you can actually use that count of mollusks per square meter as an age measurement, because you can point to it on a graph. You can find an example where you can date it in other ways. So a lot of things to do with dating in geology is to do with cross multiplying or like cross-referencing lots of different dating methods. Same in archaeology. And if you can put some pins in the map, as it were, to work out how many mollusks per square meter per century is it. And interesting, we were talking about gooey ducks earlier. This is being done for gooey ducks in the Pacific Northwest. You can work out how quickly they repopulate. Then you can work out how old something is. And so there's techniques like that. But specifically, I don't know. But they will have techniques, geological techniques and geobiological techniques that can establish age. To do with also to do things like on land, you can do things like there are radiometric dating techniques that date lichen and moss, and so you can work out how old things like walls are. So like dry stone walls that can be like centuries old, maybe in some places millennia old. You can work out how long they've been there by dating lichen from different surfaces of the rock. Yeah, possibly, Boo, but if the situation is the same, like if you've got a colony of mollusks here and a colony of mollusks here, they're probably going to be pretty similar. Like all science is about collecting as much data as possible and then doing good analysis. The more data you have, the better. The better analysis you do, the better. It's all about homing in on an answer. There's no magical bullet. The more work you do, the more accurate you get. And so initially, as I was saying, you might only be able to do relative dating. A lot of dating in geology and archaeology is purely relative. This is older than that. That's as good as you can do. And then you start to put some pins in it, like, oh, well, we've got some carbon dating from this layer, so we know how old this layer is approximately. We know how old this layer is, and so we can interpolate. And you start to be able to put some pins in it. That's a process you have to go through gradually. Yeah, exactly, Grant. That's what I was talking about earlier with the child who'd like literally just done it in geography class the week before, saving the family because they were like, oh, hang on a minute. You know, Mrs. Smith told us about that last week. Yeah, exactly, Silva, exactly. So volcanoes have chemical signatures. And so when you look at ash, sometimes you can tell exactly which volcano produced that ash. They have fingerprints, chemical fingerprints. And so you see a few ash layers, you can go like, oh yeah, this one came from that volcano, this one came from that volcano. Yeah, so that's called the law of, what Viper is describing is called the law of superposition. So if you have sediments being laid down gradually, or suddenly actually, the lower down ones will be older than the upper ones. Not rocket science. And so anything that's in one of those lower layers is likely to be around the same age as, always true, likely to be around the same age as the sediment that surrounds it, or at least the formation of that sediment. And so if you have a lump of tree wood that's stuck in a sediment, it got there because it got stuck in the sediment, or it grew in the sediment. And so when you have like a layer of coal, for example, that layer, that forest, is the same age as the rocks that are above and below it, because that's when it was growing. So you can work a lot of things out relatively. The trick is trying to pinpoint exact dates. That's difficult. And quite often in geology and archaeology, which share a lot of similarities, you just can't do that. Best you can do is, just because you just don't know, all you can do is say like, it's around about this old and this one's older than that one, but that's all we can do. And so it's very difficult. In archaeology, they need very specifically datable artifacts like coins that are from a very specific period, or certain types of pottery. But in order to learn which pottery is from which part of this civilization's history, that has to be built up over a long time. You can't walk into a dig and go like, oh yeah, there's some pottery. Oh, that's 640 BC, because in order to come to that conclusion, you have to map out the entire history of pottery in that civilization. And that's the work of centuries. It's the same with geology. Building up the stratigraphy takes a lot of work and a lot of time. And so it's really important that geologists in general are adding to that data pool. And this goes for all sciences. Even though an individual contribution to science might seem trivial, some grad student goes and draws a stratigraphy of, a rock face in Nevada somewhere. That might seem trivial. But that data goes into the big pool of geology data, and it might allow someone else to do a meta-analysis with some other studies, some other stratigraphy, and match things up. You might be like, oh, hey, well, this person saw this layer and that layer and that layer in that order in this place, and that same order of stuff appears over here, just down the road. But over here, we've got datable things. We've got things that we can radiometrically date, to put pins in it, and those dates can then be mapped back to the other place where we don't have datable material. And so now we know the dates of these. And then you can put it on a map. And then you can interpolate. So if there's another rock face or dig site or core or whatever that happens in between those two, you then know how old it is. Absolutely, all science stands on the shoulders of the previous science. It is a massive, monumental effort by the whole of humanity over multiple generations. And the longer we do it, the more we understand the natural world and the more accurate our understanding of the natural world becomes. Our ideas become more honed in, we understand the mechanics behind them better, we can make better predictions, throw crappy ideas out. Yeah, so there's actually a project, Yak actually told me about this, so there's actually a project, a citizen science project, I don't know if it's still going on. If you have a camera, an outdoor camera that can see the sky, either incidentally because it's a security camera or purposely because you've set it up to do this, you can actually register the camera with this citizen science project, and they will use your footage, and if any meteors appear in your footage, they will put yours, because they know obviously you give them the exact location of the camera. You tell them this is the GPS location and it's pointing in this direction or whatever. And so because it's a 2D image, obviously you can't tell a lot from a 2D image. But if you take lots of 2D images, and you know the location that that 2D image was taken in, just the perspective it's looking at, and you see the same meteor streaking through the sky in lots of different angles, then you can work out very accurately the trajectory of that rock. This was also done, interestingly, in what was it called? I forget the name of the Russian town. There was an airburst that happened in Russia somewhere. I forget where it was. Quite recently, relatively. And because Russia has an obsession with dash cams, Tunguska. Was it Tunguska? No, recently. Chelyabinsk. Thank you, Afsan. Chelyabinsk. Where is that? Let's find out. I'm learning. So Chelyabinsk, a few years ago, had an airburst meteor. So it came in through the atmosphere, and rather than staying solid until it hit the Earth, it actually exploded in midair. And there's amazing dashcam footage of this from a lot of drivers, because in Russia, lots and lots of vehicles have dashcams. And it's a pretty big town, city even. And so there were lots and lots of people driving around with cameras pointing at the sky, partially. And so scientists were able to... You actually have a few pieces of it. Really, that's cool. So a lot of footage was available, and so scientists went around and collected as much dashcam footage as they could. I think they set up a website where people could send it. And the local population was pretty invested in this, because this Chelyabinsk detonation blew out like windows and caused damage and injuries, and so people were kind of invested in this thing. It was sort of in the minds of the people. And so the scientists collected a lot of data, and they had so much video footage from cars, and they could like position where the cars were based on the landmarks in the footage. They could tell, okay, they're on the corner of this road or whatever. That they managed to plot the trajectory of the Chelyabinsk impactor very, very accurately. And I think I'm right in saying, Afsan might be able to correct me, that is actually how they managed to work out where it landed, because it landed out in the middle of nowhere. And so they actually used this calculated trajectory, like, oh, it went that way. Oh, it must have landed over there. And they went out into the Russian, steppes. And went and found it. Most of this is just empty. And lakes. So many lakes. Look how many lakes there are. It's like Finland. Weird landscape. Big, yeah. If you haven't seen that, you can't have missed it if you were looking at the news when it happened. Because it was all over the news. And there's a lake. It's so flat. So incredibly flat. Yeah, Sammy, I'm done too, don't worry. Ain't gonna miss much. Denmark, yeah, Denmark is also very flat. It's got some lumpy bits. Like here it's pretty lumpy. Look, slight rises. Like there's a mountain in Denmark. Look, it goes down a bit. Did I see the non-geology question? No, I did not. Please repeat it. like East Anglia. That's actually it's not quite, but looks kind of similar to where I live. Here's a bit lumpier. 170 meters. That's like Everest. What's it called? I want to see. What's it called? Is anything objective? The necessity to anything being independent of our ability to see or conceive it. Depends what you mean by is anything objective. I would I've just noticed there's a place called Bjerringbro. Let me rephrase that question. If nothing existed in the universe that had a... This is essentially, if a tree falls over in the forest, does it make a noise? And it's a philosophical question which really doesn't matter. But if there wasn't anything in the universe that had a brain, had the ability to think, would the universe exist? I think is what you're saying. Yes, I think it would. The fact that we exist doesn't change anything. And I would say that the universe is pretty objective. So this is the tallest mountain in Denmark, is it? Oh, ooh, kind of hilly. Cows. Do the heavens exist? What do you mean by heavens? Define heavens. I'm assuming that archway marks the top of Denmark. Pretty good view. Nice cows. Bird of prey. Ooh. That's quite a big bird of prey. You know what it looks like, though? This bird's like, oh man, those cows look really tasty. Oh, if only I was a little bit bigger. It's a dragon, yeah. It's a whole field of cows. Does the cosmos exist? Yes. I believe the cosmos exists. We have lots of evidence that the cosmos exists. Because it's there and we can see it. That's what you mean by cosmos. Excuse me, cow, what were you doing? I love how they're so curious. I really like cows. I believe these are Jersey cows. Scotland used to have dragons until the unicorn saved everyone. Evidence was understood by us? Yes. What is your point? If your point is things can't exist unless we think of them, I think that's silly. Because that is obviously not true. Where's the highest point in the Netherlands? Netherlands highest. Vjalsburg. Vjalsburg? Ooh, that looks a bit more lumpy. Oh, there's trees. Also, I'm a bit in a box. Get a better view somewhere. Oh, there's gonna be trees everywhere. Dang it, trees. That's practically Germany. In fact, half of it is in Germany. That bit is in France? Luxembourg? Where is that? Belgium. It's kind of cheating, honestly. We can see from this giant road. Nope, there's still trees. So what have we learned about this part of the world? There's lots of trees. And a fire engine. I'm not anti-tree, they just get in the way. The highest mountain in the UK is Ben Nevis. It's extremely lumpy. Ben Nevis. That is the highest peak in both the UK and Scotland. The highest peak in England is Scafell Pike. Is there. And looks a bit like this. And the highest point in Wales is Snowdon, or Eryri as it's known. Wasn't it? Actually, this is Iroidva. I don't remember which one's which. Am I right? Yeah. Yes, Iroidva is the name of the mountain. Eryri is the name of the region. Yes, it has a funicular railway. You can literally take a train to the top of Snowdon. It's also way too busy. This is not... If you want to go mountain climbing in North Wales, don't go to Snowdon. I highly, highly recommend the Glitters, which is just opposite. So do Glitterflower instead. It's much better. It's a 3. If you're a experienced mountain climber, you can do Triven, which is this one, which is beautiful. And then you can go across this ridge and then up to Glittervawr and Glittervach. It's a beautiful, beautiful walk. You can do a loop from down by the lake here and come up around. Stunning. Look at that for a view. Like proper Lord of the Rings stuff. Some then Ogwen. This ridge here cured me of my fear of heights. Before I did this for the first time, I was terrified of heights, and then I had to go across that. I am no longer afraid of heights. He looks cold. Bloody ninja. He could fight a proper villain, yeah, absolutely. The rocks here form these like really angular like shapes. Always makes I love it. It looks like dragon scales or something. It's amazing. Oh yeah. And then if I go just the other side, we should be able to see Snowdon from Glitterford. At night time, apparently. Ooh, good morning. Yeah, Snowdon is that one, I think. And it's my favorite place in the whole world. Oh, it's a poopy place. Nearly. Cata Idris. Why are all these V-spots so poopy? There we go. Oh man, it's so pretty. Who stole all the trees? Altitude. Altitude and terrible soil. Out of interest, you know we were talking about pillow lava earlier? Just the other side of here, there's pillow lava. But they are upside down. I thought that was a child then, it's a backpack. Peeps. I have sheltered in there many times going, oh my god, it's raining. We're going to die. On a really clear day from up here, and I've seen this a couple of times, on a really clear day, you can see, so this is the Hlain Peninsula. So this part here is, so we're in here. And looking over, this is the Hlain Peninsula here. But you can actually, if you look past that on a clear day, you can actually see the Isle of Man. Believe it or not. And Island. So if you can't see it, this is way too cloudy, but in, probably in there, you can just see the Isle of Man, just plonk, just sitting in the middle of the RC. And if you look over that way, you can see Island on a very clear day. Is this the mountain range that's also in America? No. I'm not sure where originally this was. The mountains in North Wales are very old. And so consequently they're very messy and they've been messed up in a lot of different orogenies. So mountains that have been fresh mountains that have then been like crunched and turned into other mountains and buried and brought back up again. And it's all very complicated. So it's kind of a complicated question to answer. It depends kind of which exact bit you look at. In some senses, probably yes. But not in quite the same sense as the other one we're talking about. It's old drovers' huts then. Imagine coming up here and living up here with the sheep every day. Crazy. Because while this looks nice now, please believe me when I say the weather up here can get insane. I've been up here when it's been snowing. I've been up here when there's been like 80-mile-an-hour winds. And there is a point here. Probably probably isn't going to get close enough to the edge to really show it. Just here. Yeah, it's not going to get close enough to the edge. There. If you would stand there, don't stand there. But if you do stand there, the wind is coming from over there. Basically coming from the Caribbean. Come a long way to push you off that cliff. And it will. Because it comes up this slope from the Caribbean in big gusts. And it can go from nothing to yes in a fraction of a second. And you're standing there, completely still air. And then suddenly you're being pushed off. And people die here all the time along this edge. Because there's on the other side of that is literally a cliff. And they just die. So don't do that. That was up there. So if you're up here and the wind is coming from behind you, don't go near the edge. Not a good plan. Because you'll end up down here. This right here is my favorite spot on Earth. Look at it. How often does that happen? Quite often. At least once a year, unfortunately. Look at it. It is just... Oh, I can't describe to you what it's like to be here, especially when the weather is bad. Beautiful when the weather is nice, but when the weather is bad up here, it's just poetic. Got this 2D flat image doesn't really do this justice. The scale of it and it's very oppressive because you're just completely surrounded by rock. It's I love it. Beautiful. So that's there. Is it good fishing? No, there's no fish in it that I know of. This probably is. So the peak of Penagata is 850-ish. That lake shore is like 500. And then you didn't miss it. I'm literally ending right now, Casey. My voice is fecked. I've been talking for 6.5 hours. However, the entire VOD is on both Twitch and YouTube, so feel free to go and watch it. Yeah, so to do this walk, you start down here. So you're going from pretty much sea level, almost sea level. So it's that 100. Is that 100? 100. You're going from about 100 meters. So it's a 680 meter climb. What do I notice about Casey's partner badge that is a partner badge? It's a partner badge. Was that first try? Did you get that first try? That's impressive. Congratulations, it took me 5 attempts. Yeah, so this is a 780 meter climb. But it is my favorite place in the world. Amazing. Raids counting? Yeah, that's true. That's really positive actually, because like it never made sense to me. Because I got started by a couple of kind other streamers giving me big raids and then like sort of kickstarting things. But I always used to get really frustrated because like I'd see these really big numbers from those streams. And I'm like, oh, but that doesn't count. So so it's good now that you get that. Because like a raid is a raid, right? So if someone cares enough to raid your channel, there must be a reason that they've done that. People raid random channels, sure, but there must be a reason why they chose your channel. Did I go to Colorado? No. No. I was mostly in northwestern Pennsylvania. Did a bit of traveling around this region. Up to the lakes, into Ohio, a bit down into the hills and mountains down here. Up into Canada. Spent a bit of time up in the Pacific Northwest. But didn't really do any of this bit. It's summer? Mm. Yeah, Casey, so the VOD is obviously going to be much easier to scrub through on YouTube. So obviously it's a live, so if you go onto my channel and go to the live tab, it should be once I finish the most recent one. It's titled pretty obviously, it's called Live on Twitch Tsunami Q&A. Feel free. We've been talking about tsunamis and all sorts of other things, including morality and objective stuff. And volcanoes and what else did we get distracted into? Oh, Greenland ice sheet, and yeah, there were a few tangents, but we mostly got there. Santorini. We get some Santorini seismographs. Live? Is that a thing? What? Huh? What? Didn't know this was a thing. Huh. That's very cool. Ah, look. Rumbly rumbly. When was that? The 29th. I think this is the one that caused the evacuations that we're currently seeing. It won't have Twitch chat, no. But I intentionally tried to repeat the question to a certain extent. So that, because I'm aware of the fact that the chat isn't there. Whereas if you watch the VOD before it expires on Twitch, actually while the VOD is still on Twitch, I could actually download a copy of this with the chat and embed it on the screen. I might do that. Because that's not too difficult for me to do. Because I have a tool that lets me download the chat as a video, which is cool. Why are we talking about tsunamis? Because a few days ago there was an 8.8 earthquake. I'm not going to repeat the whole stream because I will literally lose my voice. But there was an 8.8 earthquake here, which caused a tsunami, which traveled out across the whole of the Pacific. Yeah, it's a tool that's on GitHub. I'll quickly show you actually. In case you might find this useful. Yeah, okay, fine. Okay. It's called Twitch Downloader. You find it on GitHub. But it's just an installer that you download. And it allows you to put in the URL of various things on Twitch. So whole VODs, clips. You can also download the chat from a particular VOD or clip. And then once you've downloaded the chat as JSON, you can actually render that chat as a video. And so if you want to, like, for example, if I want to take this stream video and I want to put it up on YouTube, but with the Twitch chat replay, so that people can see what questions, because I didn't put it on the screen, so I'd have more screen space. I can download the VOD as a video, an MP4, which for a 6-7 hour stream is obviously going to be huge. And then I can download and render the chat into a video that I can set the width and the height for. I can choose the font and everything to put it wherever I intend to have it on the screen. And then I can just put that into some editing software. And in my case, that's Premiere. And just render it into a single video. Because if I, you know, the VOD will be a certain length, the chat will be the same length. And so in theory, they should sync up. So as long as if I'm doing any editing, cut out, you know, breaks and stuff. As long as I make sure I slice through the chat and the video, it all stays in sync. So the chat download, which gives it to you as a JSON, that has obviously timestamps. And so that when it renders out the video of the chat messages appear in the chat video at the same time they appeared in the real chat. And so it's a replay of the chat in real time, which is very useful sometimes if you have to do things like this. Yeah. Twitch downloader version 1.5-ish. Very useful. And you can queue up lots of things at once. So if you have to download a bunch of VODs to edit them, you can queue them up and it'll go through and download them all in the background. It's been very handy occasionally to have. Oh god, boo, it's 2:30 in the morning. So are there good examples of how something would exist without anything having any way to conceive of it? When I die, the moon is still there. If everyone dies, who gives a shit? There's no one to notice whether it goes poof or not, so who cares? Might you suggest drinking some liquids that help soothe your voice and throat? So I don't know whether you noticed, but I've drank a pint of lemon and ginger tea. I will probably drink another pint of lemon and ginger tea with some actual ginger and some actual lemons in it. Don't you worry, be fine. Tomorrow I might be a bit light on the talking. Be fine. Object permanence alert. What you're wondering about? Yeah, it's one of those philosophical questions I don't think it's worth putting any effort into because it's A, doesn't affect anything, and B, it's impossible for us to ever realize. Because if every thing that we can communicate with that has consciousness disappears, there's nothing around to communicate with, and so no one will know anyway. The only existence that we can ever think about is an existence where we can think. So thinking about anything else we can't ever achieve because it's impossible is not worth thinking about. Because it's pointless. Go to bed, Viper. I should go to bed too. Well, at least go and get some food. All right. Thank you very much for your attention. And we probably won't do this again for a while, but we might do it at some point. Although I keep covering the same thing over and over again, so... maybe we could talk about rivers at some point, that'd be cool. Talk about heckin' rivers. Well, I was hoping, Casey, that because it's Saturday, you might be able to rock up, but oh well, never mind. Oh well. Are we gonna raid? Is anyone doing science? Live earthquakes? Wait a minute. What is this? There's a live earthquakes channel? Okay, we're doing that. I don't know this channel. I don't recommend this channel. I haven't watched this channel, but it is a live map of earthquakes, apparently. We're going to go there so that you know that it exists. Was there a specific area I did my research to make training as a geologist? Yes, glacial geology. So in the UK, I don't know where you're from, but in the UK, compared to, say, the American system, our degrees are done on a single topic. So whereas an American bachelor's degree will cover lots of different topics, like so the American university system, the bachelor's degree is more like an extension of high school, right? So you're covering lots of different topics, and it's a very good general education. And then you decide to major in something, maybe major in two things. But it covers a lot of different stuff, and that one topic. So when an American says, I have a bachelor's in this, what they really mean is, I did a university degree and I focused on this, which is not a bad thing. It's just different. Our degree is the opposite. So our degree is, if you study maths, you just study maths. You don't do anything else. So you're completely ignorant when it comes to everything else, but you really, really know maths. And so, for example, at the end of my first year of my geology degree, I went to the States. I knew more about geology as a first year geology student from the UK than graduate students from the US, but they knew a butt-ton more than I did about everything else. So it's a really weird situation to be in, because they knew like maths and statistics and languages and sports and like loads of different things. And so our degrees are much more specialist, and some degrees in other countries are much more generalist, and everywhere in between. So yeah, my degree is in, well, my first degree is in geology, with a specialization in glacial geology. And that's all I studied, geology. Yeah, the different systems with different focuses. Right, let's raid this this thing you do. I do have follower only chat, which I don't like, but oh well. You try to play hooky, okay. There we go. I've set up the raid, and we will go up to YouTube and end that stream. Bye. That was bye to YouTube.